There's something unsettling about the way the past reveals itself, not all at once, but in fragments like pieces of a puzzle that never quite fit together. You find precision where there should be error in tension, where there should be randomness and patterns that seem to repeat without any clear connection. It doesn't feel like coincidence. It feels like alignment, like everything is pointing somewhere. But the direction has been lost, and the deeper you look, the more it begins to feel intentional. As if what remains isn't everything that existed, but only what was meant to survive. And that changes everything. Because the question is no longer what ancient civilizations built, but what they chose to leave behind. Rising from the arid plains of northern Jordan, al-Jimal appears at first glance like a city carved from shadows, its buildings constructed almost entirely from dense black basalt, a volcanic rock notoriously difficult to shape even with modern tools. Archaeological evidence suggests the site was occupied from the 1st century CE through the Byzantine period, with major development between the 4th and 7th centuries. Excavations conducted since the early 20th century, including surveys by Howard Crosby Butler in 1905 and later systematic studies by Bert de Vries in the late 20th and early 21st centuries, have documented more than 150 structures, houses, churches, barracks and towers, many of which still stand to multiple stories. Yet beyond its impressive preservation, al-Jimal presents a deeper mystery. The technological capabilities required to construct such a city using one of the hardest building materials available in the ancient world. Basalt, with a compressive strength often exceeding 100 to 300 megapascals, is significantly harder than limestone, the primary material used in monuments like the pyramids of Egypt. Cutting, shaping, and transporting basalt requires immense effort. Even today, industrial diamond-tipped tools are commonly used to achieve precision. Yet at al-Jimal, ancient builders managed to quarry, shape, and assemble thousands of basalt blocks with remarkable consistency. Yet many walls were constructed using dry stone techniques, stones fitted so precisely that mortar was unnecessary, suggesting a level of craftsmanship that challenges conventional assumptions about the technological limits of the period. However, it is not the walls themselves that raise the most profound questions, but rather the architectural elements that seem almost impossible given the constraints. The massive stone doors and monolithic stone roofs. Among the most striking features uncovered during archaeological surveys are the basalt doors, some weighing several hundred kilograms, carved from single slabs of stone and mounted on pivot hinges also made of stone. Unlike wooden doors, which rely on metal hinges and degrade over time, these doors were engineered to rotate smoothly within carved sockets in the threshold and lintel. Yet, in several structures, these doors remain functional even after more than 1,500 years of exposure. This raises immediate technical questions. How are such heavy slabs precisely balanced to allow rotation? The pivot points would have required exact alignment to within millimeters. Any deviation would have rendered the door immovable due to friction and weight. Experimental archaeology has attempted to replicate such mechanisms, yet achieving the same durability without modern materials remains extremely challenging. Comparatively, similar pivoting stone doors are rare but not entirely unique in the ancient world. Examples exist in Nabatean sites such as Petra and in certain Roman structures, but the scale and frequency at al-Jimal are unusual. In Petra, for instance, most doors were wooden, and stone was reserved for decorative or structural framing. At al-Jimal, however, stone was not just structural. It replaced organic materials entirely, likely due to the scarcity of timber in the region. This adaptation, while logical, required a radical rethinking of architectural mechanics. A basalt door measuring approximately 1.8 meters in height, 0.8 meters in width, and 0.15 meters thick could weigh upwards of 400 to 600 kilograms. The ability to install such a door so that it opens and closes with manageable force implies a deep understanding of weight distribution, rotational mechanics, and material stress, concepts that are rarely attributed explicitly to builders of this era. Equally perplexing are the stone roofs found in many of the surviving structures. Rather than using wooden beams to support lighter roofing materials, builders at al-Jimal employed long basalt slabs laid horizontally across walls to create ceilings and upper floors. Some of these slabs span distances of over 2 meters and weigh several tons. From a structural engineering perspective, basalt is strong in compression but brittle under tension. Improper placement or uneven loading could easily result in catastrophic failure. Yet many of these roofs have remained intact for centuries, surviving earthquakes, temperature fluctuations, and erosion. This suggests not only careful selection of stone with minimal internal flaws, but also precise calculation of load distribution across supporting walls. Archaeological studies have noted that the spacing of walls and the thickness of supporting structures appear optimized to handle these heavy loads. In some buildings, walls exceed 1 meter in thickness, providing the necessary stability to support multi-ton slabs. However, no written records or construction manuals have been discovered to explain how these calculations were made. Unlike Roman engineering texts such as those by Vitruvius, which detail construction principles, the builders of al-Jimal left behind no such documentation. Their knowledge, it seems, was either transmitted orally or has been lost entirely. The question of transportation further deepens the mystery. Basalt is not only difficult to shape but also extremely heavy, with a density of around 3,000 kilograms per cubic meter. Moving large stone slabs from quarry sites to construction areas would have required coordinated labor and possibly mechanical aids such as rollers, sledges, or lever systems. Yet the archaeological record provides limited direct evidence of such tools. No large-scale lifting machinery or mechanical systems have been found at the site, leaving researchers to infer methods based on indirect clues. The precision with which these heavy elements were placed, particularly in elevated positions, suggests a high level of organization and planning. Modern experiments attempting to recreate such structures using only ancient techniques have encountered significant difficulties. Even with teams of skilled workers, replicating a functioning basalt pivot door or installing multi-ton stone slabs without modern machinery proves time-consuming and prone to error. This gap between experimental results and ancient achievements fuels ongoing debate. Were these builders simply more skilled than we assume, or have we underestimated the technological sophistication of so-called pre-industrial societies? Beyond the mechanical challenges, the durability of these structures adds another layer of intrigue. Basalt is highly resistant to weathering, but the integrity of moving parts, such as pivot hinges, would typically degrade over time due to friction and environmental factors. Yet many doors at al-Jimal show surprisingly little wear. This could indicate the use of lubricants, surface polishing techniques, or even lost material technologies that reduce friction and prolonged functionality. However, definitive evidence for such practices remains elusive. In the broader context of ancient architecture, al-Jimal stands apart as an example of adaptation to extreme environmental constraints. Where other civilizations relied on wood, builders here turned entirely to stone, not just as a substitute, but as a fully integrated mechanical system. This required innovations that blur the line between architecture and engineering. When compared to more famous sites such as Roman cities of the Mediterranean or the Nabatean capital of Petra, al-Jimal lacks monumental grandeur, yet its technical solutions may be even more remarkable precisely because they operate within stricter limitations. What do you think? Are the stone doors and roofs at al-Jimal the result of lost ancient technology, or are we underestimating the capabilities of ancient humans? Where are you watching this video from, and what time of day is it for you? Share your location and time in the comments below. Hidden deep within the arid expanse of northwestern Arabia, the ancient oasis of AlUla emerges not merely as a survival point in the desert, but as a sophisticated, long-lasting experiment in environmental engineering, material science, and architectural resilience, one that continues to puzzle archaeologists and engineers alike. Over the last several decades, systematic surveys and excavations led by the Royal Commission for AlUla, alongside international archaeological missions, have revealed that this region sustained continuous human occupation for more than 6,000 to 7,000 years, with significant urban development flourishing during the eras of the Dadaean and the Lycian Kingdom around the 1st millennium BCE. Yet beyond its impressive antiquity, and what makes AlUla truly extraordinary is the silent evidence of a technological system, particularly in architecture, that appears far more advanced than what conventional historical narratives would suggest. At the core of this mystery lies the architecture of earth and stone, a domain where AlUla seems to defy both expectation and replication. Unlike monumental civilizations that relied heavily on carved granite or marble, the builders of AlUla worked primarily with mud brick and sandstone, materials typically associated with impermanence. And yet, paradoxically, many of these structures have endured for over 1,500 years, with some foundational elements possibly dating even further back. This endurance becomes even more astonishing when one considers the environmental conditions. Extreme thermal fluctuations that can exceed 40 degrees Celsius between day and night, seasonal flash floods capable of eroding entire landscapes, and constant wind-driven sand abrasion acting as a natural sand-blasting force over centuries. In comparison, other ancient mud brick cities, such as Mohenjo-Daro of the Indus Valley Civilization, dating to around 2500 BCE, have required continuous conservation efforts to prevent deterioration caused by salinization and erosion. Even then, large portions have degraded significantly over time. Similarly, mud brick settlements across the Sahara or Arabian interior often collapse within a few centuries if left unmaintained. Yet in AlUla, entire wall segments, alleyways, and structural outlines remain visible and, in some cases, surprisingly intact despite long periods of abandonment. This anomaly has led researchers to question whether the apparent simplicity of mud brick construction here conceals a far more advanced understanding of material composition and structural behavior. Recent material analyses suggest that AlUla's builders may have employed layered composite techniques rather than uniform brick mixtures. Instead of relying solely on clay and water, they appear to have incorporated sand of varying grain sizes, organic fibers such as plant matter, and possibly mineral stabilizers to enhance tensile strength and resistance to cracking. This multi-component approach would have allowed the bricks to behave more like flexible composites, capable of absorbing stress caused by thermal expansion and contraction, a concept remarkably similar to principles used in modern engineered materials. However, despite controlled laboratory experiments attempting to reproduce these mixtures, researchers have yet to fully replicate the durability observed in the original structures, suggesting that subtle variables, perhaps related to local soil chemistry or preparation methods, remain unknown. Equally compelling is the integration of stone architecture, particularly in more prominent or strategically important structures. Sandstone blocks, sourced locally, were cut and assembled with a level of precision that challenges assumptions about the tools available at the time. While not as visually monumental as the rock-cut facades of Petra, there the craftsmanship reveals a comparable understanding of load distribution, joint stability, and long-term erosion resistance. In some cases, the joints between stones are so finely aligned that mortar appears minimal or entirely absent, a technique reminiscent, though less elaborate, of the dry stone masonry seen in Machu Picchu, where interlocking blocks have withstood seismic activity for centuries. The question arises, how did a desert-based society, with no known access to advanced metal tools or written engineering manuals, achieve such precision? Beyond the materials themselves, the architectural design of AlUla demonstrates an intricate relationship with environmental physics. Settlements were densely clustered, with narrow passageways and high walls designed to maximize shade and channel airflow. This configuration creates a passive cooling system capable of reducing ambient temperatures by an estimated 5 to 10 degrees Celsius, a level of efficiency comparable to modern sustainable urban design. The orientation of buildings appears to have been carefully calibrated to minimize solar exposure during peak heat, while capturing prevailing winds, suggesting a deep empirical, or perhaps even theoretical, understanding of microclimatic dynamics. Such integration of architecture with environmental control further reinforces the idea that these were not ad hoc constructions, but the result of a refined and possibly standardized knowledge system. Excavations carried out between 2018 and 2023 have added yet another layer of complexity. Beneath visible ruins, archaeologists uncovered multiple construction phases, indicating that structures were repeatedly modified, reinforced, and rebuilt over centuries. This pattern implies not only long-term occupation, but also the existence of a continuity of technical knowledge, likely transmitted through generations without reliance on written documentation. Unlike ancient Egypt or Mesopotamia, where architectural practices were sometimes recorded in texts or inscriptions, AlUla offers almost no direct written explanation of its construction methods. This absence transforms each surviving wall and foundation into a kind of silent record, one that must be interpreted through physical evidence alone. Comparative studies with other desert regions deepen the enigma. In North African Qasars, for instance, similar mud brick techniques are still used today, but require constant maintenance to prevent structural failure. In contrast, many AlUla structures have remained recognizable after centuries of neglect, suggesting either superior initial construction or uniquely favorable preservation conditions, or perhaps a combination of both. Some researchers propose that the oasis environment itself created a microclimate that slowed degradation, balancing humidity, temperature, and airflow in a way that preserved materials more effectively. However, this hypothesis does not fully explain why certain structures are significantly more resilient than others, even within the same environment. Ultimately, AlUla Ancient Oasis challenges our understanding of advanced technology. With no machines or written plans, thus its builders still mastered water control, environmental adaptation, and durable construction in ways modern science cannot fully explain. In the silence of the desert, AlUla endures, not as ruins of a simple past, but as evidence of a sophisticated knowledge system that has yet to be fully rediscovered. If you could travel back in time to the era of AlUla Ancient Oasis, what do you think would surprise you the most? Their construction techniques, their environmental management, or the knowledge they never recorded? Share your thoughts in the comments below. Rising from the windswept plains of southern Tunisia, Ksar Ouled Sultan stands as one of the most visually striking and technically puzzling desert structures ever documented. At first glance, it appears to be a simple fortified granary, rows of compact earth-toned storage chambers known as ghorfa, stacked vertically around a central courtyard. Yet this seemingly humble complex, constructed between roughly the 15th and 18th centuries, conceals a level of engineering sophistication that challenges modern assumptions about pre-industrial construction, particularly when examined through the lens of material science. Located in a region where daytime temperatures frequently exceed 40 degrees Celsius, and seasonal winds carry abrasive sand capable of gradually stripping away exposed surfaces, the Ksar should, by all conventional expectations, have eroded into near ruin within a few generations. Instead, large portions of the structure remain intact after several centuries, raising a fundamental question. How did a civilization relying on such seemingly simple materials achieve such extraordinary durability? The answer, or rather the mystery, begins with the very substance from which the Ksar is built. The walls consist primarily of a mixture of clay, water, and organic fibers such as straw, materials that form what is broadly classified today as adobe. In modern construction, adobe is widely regarded as a low-cost, low-strength material. Even under controlled conditions, untreated adobe bricks typically exhibit compressive strengths ranging from 1 to 2 megapascals and are highly susceptible to erosion, particularly in environments with fluctuating temperatures and persistent wind exposure. Modern stabilized adobe, reinforced with cement or chemical additives, can achieve higher durability, yet even these improved versions often require regular maintenance to prevent cracking, surface degradation, and eventual structural failure. Against this backdrop, the performance of the materials at Ksar Ouled Sultan becomes deeply anomalous. Archaeological surveys conducted across the Tatooine region during the late 20th century, along with more recent conservation studies in the early 2000s, have recorded compressive strengths in preserved sections of Ksar walls ranging from approximately 2 to 4 megapascals, values that approach or even exceed those of some modern, minimally stabilized earthen constructions. More remarkably, these measurements come from walls that have endured centuries of thermal expansion cycles, ultraviolet radiation, and continuous sand abrasion without the benefit of modern protective coatings. This raises an immediate and unresolved question. What exactly is different about the material? Unlike Roman concrete, whose resilience has been partially explained through the presence of pozzolanic volcanic ash and self-healing mineral reactions, the composition of the Ksar's earthen mixture has not been fully decoded. Laboratory analyses of samples taken from comparable Ksar in southern Tunisia and Libya have revealed a complex internal structure. The clay matrix appears to contain a finely balanced distribution of particle sizes, from coarse grains that provide structural bulk to ultrafine silts that fill microvoids, reducing porosity and limiting water infiltration. Embedded within this matrix are organic fibers, primarily straw, whose role extends beyond simple reinforcement. Over time, as these fibers decompose or mineralize, they may leave behind microchannels that help relieve internal stress, reducing the likelihood of cracking under thermal expansion. Some studies have also detected trace amounts of naturally occurring salts and minerals, possibly introduced through the water or soil used during construction, which may have contributed to a subtle chemical stabilization effect. However, none of these factors alone sufficiently explain the long-term resistance of the material, and attempts to replicate similar mixtures in modern experimental settings have yielded inconsistent results. Even more intriguing is the phenomenon observed on the outer surfaces of many walls, a form of natural hardening that appears to have occurred over time. Repeated exposure to intense solar radiation and extremely dry conditions may have induced a gradual transformation in the microstructure of the material, leading to the formation of a denser, more resistant outer layer. This case hardening effect has been documented in other earthen structures, but rarely with the degree of uniformity and effectiveness seen at Ksar Ouled Sultan. In some areas, the outer layer exhibits a hardened surface strong enough to resist scratching and minor impact, while the underlying material remains comparatively softer. This dual-layer structure could act as a natural protective barrier, slowing erosion and preserving the integrity of the inner core. Yet this explanation introduces another layer of complexity. If the hardening process is purely environmental, why do similar adobe structures in comparable climates not display the same level of preservation? Comparative field studies of earthen architecture in Morocco, Algeria, and parts of the Middle East reveal significantly higher rates of degradation, with many sites requiring extensive restoration after just 1 or 2 centuries. The Qasr's relative resilience, therefore, suggests that its builders may have unintentionally, or perhaps deliberately, created a material system uniquely suited to its environment. Archaeological investigations have also focused on construction techniques, which may hold additional clues. Excavations and structural surveys indicate that the walls were not built from preformed bricks in the modern sense, but rather through a layered process of compacting moist earth mixtures directly into place. Each layer, often several centimeters thick, would have been allowed to partially dry before the next was added, creating a stratified structure with improved cohesion. This method, combined with the massive thickness of the walls, often exceeding 50 centimeters, results in a construction that is both robust and internally stable. The thickness not only enhances load-bearing capacity, but also contributes to thermal inertia, allowing the walls to absorb heat during the day and release it slowly at night. Measurements conducted in preserved Ghorfa chambers show that interior temperatures can remain 8 to 12 degrees Celsius lower than the external environment, a level of passive cooling efficiency comparable to certain modern eco-architectural designs. This suggests that the material was selected and processed not merely for availability, but for a sophisticated combination of mechanical and thermal properties. Historical documentation of these techniques, however, is virtually non-existent. No written manuals, architectural blueprints, or detailed records have been discovered that describe the precise composition or preparation of the building materials. This absence of documentation presents a significant challenge for modern researchers. In contemporary engineering, and reproducibility is a cornerstone of technological understanding. Yet in the case of Ksar Ouled Sultan, the knowledge appears to have been transmitted through oral tradition or practical apprenticeship, systems that are inherently vulnerable to loss over time. The consistency observed across different sections of the Qasr implies a high degree of standardization, suggesting that the builders possessed a reliable method for achieving the desired material properties. How this consistency was maintained without written guidelines remains an open question. Adding to the mystery is the broader context of similar structures across the Maghreb region. While Qasr are not unique to Tunisia, the level of preservation and apparent material optimization seen at Ksar Ouled Sultan places it among the most exceptional examples. Comparative studies between different Saur have shown variations in material performance, even when constructed using ostensibly similar ingredients. This variability implies that subtle differences in soil composition, water source, mixing ratios, or curing conditions could have a profound impact on durability, factors that ancient builders may have understood empirically, even if not scientifically articulated. In this sense, the Qasr represents not just a single structure, but the culmination of a long process of environmental adaptation and material experimentation. What do you think? Is this simply the result of centuries of accumulated experience, or evidence of an ancient technology that modern humans still cannot replicate? Share your thoughts in the comments below. Hidden deep within the stark, sun-scorched landscape of southern Oman The ancient valley of Wadi Dawkah preserves one of the most enduring and least understood natural phenomena of the ancient world. Scattered across this UNESCO-listed site are the resilient trees of Boswellia sacra, a species that has, for thousands of years, produced frankincense, a resin so prized that it once rivaled gold in value and shaped entire trade networks stretching from Arabia to the Mediterranean and beyond. Yet beyond its historical importance lies a deeper mystery, one that modern science has only partially unravelled: the astonishing chemical complexity of frankincense itself, and the persistent inability of advanced technology to fully replicate it. Archaeological expeditions conducted throughout the Dawkah region, particularly from the 1990s onward under UNESCO's Land of Frankincense programme, have revealed that Wadi Dawkah was not merely a passive natural resource, but the centre of a highly organised and technologically sophisticated system of cultivation and extraction. Evidence from excavations, including stone tools, carved tapping marks on ancient tree trunks, and the remains of caravan routes, suggests that frankincense harvesting was already systematised as early as the first millennium BCE. At sites such as Khor Rori, ancient Sumhuram, archaeologists uncovered storage vessels containing resin residues, along with inscriptions referencing trade quantities and taxation. These findings indicate that ancient harvesters possessed not only practical knowledge of tree physiology, but also a standardized method of extraction that optimized yield while preserving long-term sustainability. Experimental reconstructions in the early 21st century demonstrated that improper incisions, too deep, too frequent, or made at the wrong season, could reduce resin output by up to 50% or permanently damage the tree. Yet ancient techniques, preserved through oral tradition, consistently achieved high yields with minimal ecological impact, a level of precision that suggests a deep empirical understanding of biological systems. However, the true enigma of Wadi Dawkah does not lie solely in how frankincense was harvested, but in what it actually is. Modern chemical analysis has revealed that frankincense resin is not a simple substance, but an extraordinarily complex mixture of organic compounds. Using advanced techniques such as gas chromatography mass spectrometry, GCMS, researchers have identified over 300 individual components within samples of Boswellia sacra resin. Among these are the well-studied boswellic acids, a group of pentacyclic triterpenes known for their potent anti-inflammatory properties. Laboratory studies have shown that certain boswellic acids can inhibit key inflammatory pathways, such as the 5-lipoxygenase enzyme, by as much as 60 to 70% under controlled conditions, making them of significant interest in the treatment of chronic diseases such as arthritis and asthma. Yet even these extensively studied compounds represent only a fraction of the resin's total chemical profile. What makes frankincense particularly mysterious is not just the number of its components, but the way they interact. Unlike synthetic pharmaceuticals, which are typically composed of one or a few active ingredients, frankincense appears to function as a highly integrated biochemical system. Minor compounds, present in concentrations as low as 0.1%, can significantly influence the overall aroma, stability, and biological activity of the resin. This phenomenon, known as synergistic interaction, means that the effect of the whole is greater than the sum of its parts. Attempts to isolate and recombine key compounds in laboratory settings have consistently failed to reproduce the full spectrum of properties observed in natural resin. Synthetic versions may mimic certain aspects, such as scent or anti-inflammatory activity, but they lack the depth, persistence, and subtle variability that characterize authentic frankincense. Comparative studies further highlight this uniqueness. For example, myrrh, another ancient resin derived from Commiphora species, contains fewer than 150 identified compounds and exhibits a more stable chemical profile across different samples. As a result, it has been more successfully approximated using synthetic chemistry. Frankincense, by contrast, remains resistant to such replication. Analyses conducted between 2005 and 2018 showed that even samples taken from the same tree at different times of the year could vary in composition by as much as 25 to 30%, depending on environmental conditions such as temperature, humidity, and soil composition. This variability poses a significant challenge for standardization, a cornerstone of modern chemical manufacturing. Archaeological evidence adds another layer to this mystery. Residue analysis from ancient storage jars found at Sumaram and al-Balid indicates that the core chemical signatures of frankincense have remained remarkably consistent over at least 2,000 years. Isotopic studies suggest that the resin traded in antiquity is chemically comparable to that produced today, despite centuries of climatic fluctuation and environmental change. This raises important questions about the stability and resilience of the Boswellia sacra species. How has this tree maintained such a complex and finely balanced chemical system over millennia? And why has evolution favored such a multifaceted composition, when simpler biochemical strategies might have been sufficient for survival? From a technological standpoint, the inability to fully replicate frankincense represents a significant limitation. In an age where scientists can synthesize complex molecules, engineer genetic sequences, and design advanced materials at the nanoscale, the fact that a naturally occurring resin remains beyond complete reproduction is both surprising and revealing. It suggests that certain natural systems, particularly those shaped by long-term ecological interactions, may possess levels of complexity that are not easily reducible to human-designed processes. Some researchers have even proposed that frankincense should be viewed not as a single product, but as a living chemical system, one that reflects the dynamic interplay between organism and environment. This perspective challenges conventional assumptions about technology and knowledge. Ancient civilizations, though lacking modern analytical tools, were able to identify, harvest, and utilize frankincense with remarkable efficiency. They developed trade networks spanning thousands of kilometers, established quality classifications based on color and purity, and integrated the resin into religious, medicinal, and cultural practices across diverse regions. Yet the underlying nature of the substance they so highly valued remains only partially understood today. In this sense, Wadi Dawkah represents a convergence of ancient expertise and modern uncertainty, a place where empirical knowledge once flourished, but theoretical understanding still lags behind. The mystery of Wadi Dawkah lies in the gap between human observation and our ability to recreate it. Despite being harvested for thousands of years, frankincense still cannot be fully analyzed or replicated. This suggests that nature remains beyond the limits of our current understanding. If modern science still cannot fully replicate frankincense, then what do you think? We are lacking the technology, or we are lacking the understanding of nature? Share your thoughts in the comments below. Hidden within the remote sandstone massif of Gilf Kabir in southwestern Egypt, the mysterious Cave of Swimmers remains one of the most intellectually challenging archaeological sites ever discovered in the Sahara. First documented in 1933 by Hungarian explorer Laszlo Almasi, the cave is renowned for its haunting depictions of human figures that appear to float or swim across the rock surface, imagery that strongly implies the existence of water in a region that is now among the driest places on Earth. Radiocarbon dating of associated organic materials and stylistic comparisons place these paintings roughly between 6,000 and 10,000 years ago, aligning them with the African humid period, when the Sahara supported lakes, seasonal rivers, and savanna ecosystems. Yet while the environmental implications of the artwork are significant, the most profound and unresolved mystery lies not in what the cave depicts, but in how those depictions have survived with such extraordinary clarity for millennia, defying both time and one of the harshest climates on the planet. Multiple archaeological expeditions, particularly those led by German, Italian, and Egyptian teams during the 1990s and early 2000s, have undertaken detailed pigment analysis using techniques such as X-ray fluorescence, XRF, Raman spectroscopy, and microscopic stratigraphy. These studies reveal that the pigments are primarily derived from iron oxide minerals, including hematite and ochre, which produce the dominant red and brown tones visible today. In some darker outlines, traces of manganese compounds have also been identified. On a purely compositional level, this does not appear unusual. Similar mineral pigments were widely used across prehistoric sites, including Lascaux Cave in France and Altamira Cave in Spain. However, it is precisely this similarity that deepens the mystery. If the raw materials are comparable, why is the preservation in the Cave of Swimmers so exceptionally superior under far more extreme environmental conditions? To understand the anomaly, one must consider the environmental context. The Gilf Kebir Plateau experiences daytime temperatures that can exceed 45 to 50 degrees Celsius, with rapid nocturnal cooling that creates continuous thermal stress on exposed surfaces. In addition, the region is subject to persistent aeolian erosion, where wind-driven sand acts as a natural abrasive, gradually wearing away exposed rock and any material on its surface. In such conditions, modern paints, even those engineered for durability, would typically show significant degradation within decades or centuries, not millennia. Yet in the Cave of Swimmers, many figures remain sharply defined, with pigment layers that have neither fully flaked away nor faded into obscurity. Some outlines retain a level of contrast that suggests minimal chemical breakdown, raising a critical question. What binding agents or application techniques were used to achieve such resilience? Conventional archaeological assumptions propose that prehistoric artists mixed mineral pigments with organic binders such as animal fat, blood, plant gum, or egg-based emulsions. These substances can indeed improve adhesion and color intensity, but they are also highly susceptible to degradation through oxidation, microbial activity, and UV exposure. Experimental archaeology has attempted to recreate such mixtures under controlled conditions, subjecting them to accelerated weathering simulations. The results consistently show that while these reconstructions can survive for limited periods, they fail to replicate the long-term stability observed in the Gilf Kebir paintings, especially under conditions approximating Sahara-level heat and abrasion. This discrepancy suggests that either the original formulations were more complex than currently assumed, or that additional unknown processes were involved. One of the most compelling hypotheses emerging from microscopic analysis is that the pigments may not simply rest on the rock surface, but are partially integrated into the sandstone matrix itself. Thin section studies of the cave walls indicate that, in certain areas, pigment particles appear to have penetrated the porous structure of the rock, forming a bond that is both mechanical and potentially chemical. This raises the possibility that prehistoric artists deliberately prepared the surface, perhaps by abrading it to increase porosity, heating it to alter its microstructure, or even applying a liquid medium that facilitated deeper absorption. If true, this would represent a level of material manipulation that borders on proto-engineering, far exceeding the commonly held view of prehistoric art as purely intuitive or symbolic. Comparative analysis with other Saharan sites reinforces the uniqueness of the Cave of Swimmers. In regions such as Tassili Naja in Algeria or the Anidi Plateau in Chad, Rock art also exhibits impressive longevity, but often shows more pronounced fading, surface flaking, or pigment loss. By contrast, certain panels within the Cave of Swimmers display remarkable uniformity in pigment retention, suggesting a consistent and possibly standardized technique. This consistency implies not only repeated practice, but also the transmission of specialized knowledge, whether through cultural tradition or a dedicated group of artisans whose methods have since been lost. Another unresolved aspect concerns the chemical stability of the pigments themselves over extreme timescales. Iron oxides are known for their durability, but even they can undergo alteration under prolonged exposure to environmental stresses. The fact that these pigments have remained stable for up to 10,000 years suggests that either the microenvironment of the cave provides unique protective conditions, or that the pigment mixture includes trace elements or structural properties that inhibit degradation. Some researchers have speculated about the presence of naturally occurring silica or clay components that may act as stabilizers, effectively locking the pigment in place. However, no definitive composition has been identified that fully accounts for the observed preservation. The broader implication of this mystery extends beyond the cave itself. If prehistoric communities in the Sahara were capable of developing pigment technologies with such exceptional durability, it challenges the linear model of technological progress that places advanced material science firmly within the domain of later civilizations. Instead, it suggests the possibility of localized knowledge systems, highly adapted to specific environments, that achieved remarkable results without leaving behind extensive physical evidence of their processes. As the Sahara underwent rapid desertification after approximately 5,500 years ago, many of these communities likely migrated or disappeared, potentially taking their knowledge with them and leaving only the finished products as silent testimony. The Cave of Swimmers is more than a record of a lost green Sahara. It is a technological artifact in pigment and stone that modern science still cannot fully explain. Despite decades of research, no experiment has replicated its durability or clarity. The figures may reflect memory or symbolism, but the pigments reveal something deeper: lost techniques and unexplained material knowledge. So the question remains, how did a prehistoric society create paint that could survive for 10 millennia in such an extreme environment? Share your thoughts in the comments below. Buried within the vast sandstone plateau of Tassili Nadja, Sefar City emerges not as a conventional archaeological site, but as a sprawling, almost surreal landscape that challenges the limits of how we define both nature and technology in deep antiquity. Stretching across tens of square kilometers, this immense formation of eroded rock towers, narrow corridors and cavern-like voids has often been described by explorers and researchers as a stone city, not merely because of its scale, but due to the uncanny resemblance of its structures to organized urban space, multi-level forms that evoke buildings, alleyways, plazas, and passage systems. Yet despite these striking similarities, Sefar lacks the unmistakable indicators of human construction. No consistent tool marks, no quarries, no discarded fragments of worked stone. The dominant scientific explanation attributes these forms to long-term aeolian erosion, wind-driven processes acting over millions of years, yet even within this framework, certain aspects remain difficult to reconcile, particularly the recurring sense of spatial order and the quasi-architectural coherence observed across large sections of the site. Still, while the geological formations provoke curiosity, the deeper and far more perplexing mystery lies etched and painted across the surfaces of these stones, an immense body of prehistoric imagery that may represent one of the oldest and most durable information systems ever created by human hands. Within the broader Tassili Naja complex, researchers have catalogued over 15,000 individual rock paintings and engravings, with a significant concentration around Sefar. These artworks span a vast chronological range, from approximately 10,000 BCE to 2000 BCE, corresponding to the African humid period when the Sahara was not the barren desert we see today, but a landscape of lakes, rivers, and thriving ecosystems. Early systematic study of the region was conducted by Henri Lot during expeditions in the 1950s, during which hundreds of paintings were documented, sketched, and photographed. His work brought international attention to a category of imagery now widely known as the round head style. Figures characterized by disproportionately large, often featureless heads, and elongated, almost weightless bodies. Some appear to float, others interact in scenes that suggest ritual or transformation, and a subset exhibit shapes that resemble helmets or suits, leading to persistent, if controversial, comparisons with modern astronaut iconography. While mainstream archaeology interprets these as symbolic or shamanistic representations, possibly linked to altered states of consciousness, the repetition, distribution, and consistency of these figures across hundreds of kilometers introduce a deeper question. Could these images represent a structured system of communication rather than purely artistic expression? What makes this question particularly compelling is the extraordinary durability of the pigments themselves. The Sahara is one of the most hostile environments on Earth for the preservation of surface materials. Daily temperature variations can exceed 40 degrees Celsius, ultraviolet radiation is intense, and sand-laden winds act as a constant abrasive force. Under such conditions, most organic or mineral pigments would degrade within centuries, if not decades. Yet the Tassili paintings have survived for over 8,000 years, in many cases retaining not only their outlines, but subtle tonal variations and layering effects. Scientific analyses have identified the use of mineral-based pigments such as hematite, iron oxide for reds, manganese oxides for darker hues, and possible organic binders derived from plant or animal sources. However, attempts to replicate these pigments using known prehistoric techniques often fail to achieve the same level of long-term stability, especially under simulated desert conditions. This suggests that the original creators may have employed preparation methods, such as precise grinding, mixing ratios, or heat treatment, that are not yet fully understood. In contrast, even the highly advanced pigment technologies of ancient Egypt, which produced colours lasting millennia in tombs and temples, relied on relatively controlled, sheltered environments. The exposed survival of Tassili's pigments therefore represents a technical anomaly that remains unresolved. Equally significant is the method by which these images were applied and integrated into the landscape. Rather than treating rock surfaces as passive canvases, many of the artists appear to have selected specific natural features, curves, cracks, protrusions, and incorporated them into the composition, creating a subtle three-dimensional effect. This indicates not only artistic awareness, but a form of environmental encoding, where information is embedded into the physical structure of the terrain itself. In some cases, engravings have been carved into hard sandstone with a depth and precision that imply sustained, controlled effort, using tools that have not been conclusively identified. When compared to famous Paleolithic sites such as Lascaux Cave or Chauvet Cave, the contrast is striking. Those European sites are enclosed, protected caves, where stable microclimates have aided preservation. Sefar, by contrast, is an open-air system exposed to extreme weathering, yet its visual records have endured longer in some cases than their sheltered counterparts. This inversion of expected preservation patterns raises the possibility that the materials and techniques used at Sefar were not only functional, but intentionally optimized for longevity. Beyond material science, Yes, the conceptual structure of the imagery invites comparison with early forms of data storage and transmission. Many scenes at Sefar are not isolated figures but sequences, depicting hunting, ritual gatherings and transformations, suggesting narrative continuity. Certain motifs recur with remarkable consistency across distant locations, particularly the round-head figures and specific animal forms. This repetition can be likened, in a modern analogy, to redundancy in digital storage systems, where critical information is encoded multiple times to ensure survival against corruption or loss. If we consider the possibility that these images functioned as a mnemonic or symbolic language, then their widespread distribution could represent an intentional strategy to preserve knowledge across both space and time. Or unlike linear writing systems such as cuneiform or hieroglyphics, which depend on sequential decoding, the tessili imagery may operate on a more associative or symbolic level, closer perhaps to a visual database than to a written text. Yet despite decades of study, no definitive grammar, syntax or phonetic correlation has been identified, leaving the language of Sefar fundamentally unreadable. Archaeological investigations throughout the late 20th and early 21st centuries have added further layers of complexity. Techniques such as radiocarbon dating of associated organic materials, stratigraphic analysis, and more recently high-resolution digital photogrammetry have revealed that many of the paintings exist in multiple overlapping layers. This indicates that the site was used continuously over thousands of years, with successive generations adding new images while preserving or partially modifying older ones. Such behavior resembles a form of long-term archival practice, where earlier records are not erased but integrated into an evolving system. In modern terms, it is akin to a database that is continuously updated while retaining legacy data, a concept that requires not only cultural continuity, but an understanding of the value of information preservation. The question then becomes, what information was considered important enough to be maintained in this way, across millennia, in one of the most challenging environments on Earth? Do you think the paintings at Sefar are simply ancient art, or could they actually be a lost form of information storage technology? Share your thoughts in the comments below. Rising in quiet isolation from the windswept desert near the ancient oasis of Tamar in Saudi Arabia, Al-Nasla rock has become one of the most visually striking and intellectually unsettling geological formations ever documented. At first glance, it appears deceptively simple, a massive sandstone boulder split into two nearly equal halves. But the longer one studies it, the more it begins to challenge the boundary between natural processes and something that feels eerily engineered. The defining feature of Al-Nasla is its perfectly straight vertical separation, a narrow gap that divides the rock with astonishing precision. Unlike typical fractures in sedimentary stone, where stress, pressure, and environmental forces produce irregular, jagged, and chaotic break patterns, the split here is remarkably smooth, flat, and consistent along several meters of height. High-resolution photographs and field observations show that the cut maintains a near-linear trajectory, with minimal deviation, leading many observers to compare it to cuts made by modern industrial tools such as diamond wire saws or even laser-guided systems. For a natural formation, this level of geometric perfection is not impossible, but it is extraordinarily rare. Geologists have proposed explanations rooted in known natural processes. One leading theory suggests that the rock developed a vertical joint due to tectonic stress or internal weaknesses within the sandstone layers, which then expanded over time through thermal cycling. In desert environments like Tamar, temperature fluctuations between day and night can exceed 20 degrees Celsius, causing repeated expansion and contraction that gradually widens cracks. Over thousands of years, wind erosion, especially from sand-laden gusts, can smooth exposed surfaces, potentially polishing a fracture plane. However, while this combination of mechanisms can indeed create relatively straight and smooth features, it struggles to fully account for the precision observed at Al-Nasla. In most documented cases of natural jointing, microscopic analysis reveals uneven stress propagation, microfractures, and variations in surface texture. By contrast, the surfaces at Al-Nasla appear unusually uniform, lacking the chaotic signatures typically associated with natural breakage. Equally puzzling is the rock's balance. Each half stands upright on a relatively narrow pedestal, as if deliberately positioned rather than randomly eroded. Estimates based on volume and sandstone density suggest that each segment could weigh between 10 and 15 tons, yet both remain stable despite millennia of exposure to desert winds and erosion. This raises structural questions. How did erosion isolate these bases without destabilizing the upper mass? And why do both halves exhibit such similar proportions, as though symmetry played a role in their final form? These details, while individually explainable through natural processes, collectively push the limits of probability when considered together. The mystery deepens with the presence of petroglyphs etched into the rock's surface. These carvings, depicting human figures, animals, and abstract symbols, are consistent with other forms of rock art found across northwestern Arabia. Archaeological surveys conducted in the Tamar region, particularly expeditions in the 1980s and more recent studies in the early 21st century, have established that this area was an important cultural and trade hub as far back as 4,000 years ago. Inscriptions and artifacts found nearby suggest connections to ancient Arabian and possibly even Mesopotamian trade networks. The petroglyphs on Al-Nasla indicate that the rock was not only known to ancient peoples, but likely held cultural or symbolic significance. Yet the timing remains uncertain. Were the carvings made after the rock had already split, or do they predate the division, implying that the fracture occurred later? This chronological ambiguity is crucial, because it determines whether humans merely interacted with an existing formation or witnessed a transformation of the rock itself. It is within this context that the technological mystery becomes most compelling. When we compare Al-Nasla to other ancient sites known for extraordinary stonework and precision, such as Puma Punku or Madain Saleh, we find both similarities and critical differences. At Puma Punku, andesite blocks weighing up to 100 tons were cut and shaped with such precision that their joints fit together with tolerances measured in millimeters, leading to ongoing debates about the techniques used by pre-Columbian builders. At Madain Saleh, the Nabateans carved monumental tomb facades directly into sandstone cliffs with symmetrical lines, sharp edges, and smooth surfaces that rival modern masonry. In both cases, however, there is clear archaeological context. Tool marks, construction patterns, unfinished sections, and cultural continuity that point to human craftsmanship. Al-Nasla, on the other hand, presents a paradox. It exhibits a level of precision comparable, at least visually, to these engineered sites, yet lacks any direct evidence of tools, quarrying activity, or systematic modification beyond the surface carvings. This absence of evidence does not prove the presence of advanced ancient technology, but it does highlight a gap in our understanding. If the split were artificially created, what method could have produced such a clean, continuous cut through a massive sandstone block without leaving behind debris, tool marks, or secondary fractures? Modern cutting techniques, such as diamond wire sawing, generate distinct striations and require controlled conditions, water cooling, and mechanical support, none of which are evident here. Laser cutting, while capable of producing smooth surfaces, is a product of very recent technological development and would leave thermal traces detectable under microscopic analysis. No such evidence has been conclusively identified at Al-Nasla. Yet the visual similarity remains difficult to ignore. Some researchers have explored the possibility of natural processes producing near-perfect planar fractures under very specific conditions. For example, certain types of sedimentary rocks can develop orthogonal joint systems where cracks propagate along relatively straight lines due to uniform stress distribution. In rare cases, these joints can appear remarkably smooth, especially if later modified by erosion. However, even in well-studied formations exhibiting such features, the resulting surfaces rarely achieve the level of flatness and continuity seen at Al-Nasla. Furthermore, the isolation of this phenomenon, without numerous similar examples in the immediate region, raises additional questions about its uniqueness. Archaeologically, there have been no large-scale excavations directly focused on the rock itself, but regional surveys have provided important context. Studies of the Tamar oasis have uncovered settlement layers, defensive structures, and inscriptions dating back to the 1st millennium BCE and earlier. Radiocarbon dating of organic materials in nearby sites has confirmed long-term human occupation, reinforcing the idea that Al-Nasla existed within a culturally active landscape. However, no artifacts directly link human activity to the splitting of the rock. This leaves researchers in a position where they must rely on indirect evidence, comparative analysis, and theoretical modelling rather than definitive proof. Do you think the perfectly straight split of Al-Nasla is an extremely rare natural phenomenon, or evidence of a lost ancient technology? Share your thoughts in the comments below. Along the northern coastline of Peru lies the Satura Desert, a landscape so extreme that even modern engineers would hesitate to build permanent settlements without advanced materials and infrastructure. With annual rainfall in some sectors dropping below 20 to 50 millimeters, constant exposure to saline coastal winds, and temperature fluctuations that accelerate thermal stress. This environment acts as a natural laboratory for material decay. In comparable modern conditions, untreated earthen structures such as standard adobe typically degrade within decades, suffering from cracking, erosion, and eventual collapse. Yet, scattered across this hostile terrain are the remains of ancient settlements whose structural integrity has endured for centuries, and in some cases more than 1,000 years. Presenting one of the most intriguing and least understood examples of ancient material engineering in the Americas, archaeological investigations carried out since the 20th century, including surveys in regions linked to the Moche civilization and the later Lambayeque culture, have revealed organized habitation zones rather than isolated ruins. Excavations have uncovered foundations, low stone structures, compacted platforms, and traces of buried hydraulic systems. Radiocarbon dating of organic inclusions such as charcoal fragments, plant fibers, and other residues embedded within construction layers places many of these structures between approximately 800 and 1,500 years old. This timeline is not extraordinary in itself. What is remarkable is their state of preservation. At multiple sites, near wall sections remain standing at heights exceeding 1 meter, with edges still relatively sharp rather than fully rounded by wind erosion. In controlled experimental comparisons, modern adobe exposed to similar wind velocities, often exceeding 30 to 40 kilometers per hour in coastal deserts, shows measurable surface loss within decades, typically several millimeters per year, leading to severe degradation over just a few centuries. The structures in Satura, however, exhibit significantly lower erosion rates, suggesting that their material composition or construction methods provided a level of resistance that has yet to be fully explained. At the heart of this enigma is the composition of the building materials themselves. Initial analyses indicate a mixture of clay, fine desert sand, and organic fibers, consistent with traditional earthen construction. However, detailed microscopic and chemical studies reveal a far more complex internal structure. The matrix appears unusually dense, with tightly interlocked mineral grains and a reduced pore network compared to typical adobe. This reduced porosity would limit water infiltration and evaporation cycles, both of which are primary drivers of structural failure in earthen materials. Furthermore, the distribution of organic fibers, possibly derived from local vegetation or even marine sources, suggests deliberate selection and processing rather than random inclusion. In some samples, traces of mineral salts have been detected within the outer layers, leading to the hypothesis that environmental exposure itself may have contributed to a form of natural surface hardening, effectively creating a protective crust that slowed further erosion. When compared to other ancient material technologies, the Satura case becomes even more puzzling. Roman concrete, for instance, has been extensively studied and is known to derive its durability from a chemical reaction between volcanic ash, pozzolana, and seawater, forming crystalline structures that strengthen over time. Similarly, the baked bricks of the Indus Valley civilization achieved longevity through high-temperature firing processes that altered their internal chemistry. In contrast, no clear evidence of large-scale kilns or controlled firing has been found in the Satura desert sites. This absence suggests that the durability observed here was achieved through low-energy methods, possibly involving repeated compaction, controlled moisture content during construction, and extended curing periods under specific environmental conditions. Experimental archaeology has attempted to replicate these processes using local soils and traditional techniques, yet results have consistently fallen short. After accelerated aging tests simulating a few hundred years of exposure, reconstructed samples exhibit cracking, delamination, and surface erosion far exceeding what is observed in the original structures. Excavation data also indicate construction techniques that may have enhanced durability beyond material composition alone. Stratigraphic analysis shows that some walls were built in layered sequences, alternating between denser and more porous materials. This approach could have functioned as a primitive stress distribution system, allowing the structure to absorb and dissipate mechanical forces resulting from wind and thermal expansion. In addition, certain foundations appear slightly elevated, with subtle gradients that would facilitate water runoff during rare but intense rainfall events, associated with the periodic climate phenomenon known as El Niño. These design features suggest not only an understanding of environmental hazards, but also a capacity to integrate that understanding into long-term construction strategies. Another factor that complicates the analysis is the role of sedimentation. The Satura Desert is characterized by significant wind-driven sand movement, with accumulation rates in some periods estimated between 1 and 5 centimeters per year. Many structures were partially buried relatively soon after their use, which may have provided a protective layer against direct exposure. However, this explanation does not fully account for the preservation of exposed sections that have remained above ground for extended periods. In several surveyed sites, archaeologists have documented standing walls with minimal rounding and preserved surface details, indicating that erosion has been significantly slowed rather than merely delayed. This observation reinforces the idea that the material itself possesses intrinsic resistance properties beyond what would be expected from untreated earth. The broader archaeological context further underscores the sophistication implied by these findings. The presence of subsurface canal systems detected through ground-penetrating radar indicates that ancient inhabitants not only constructed durable buildings, but also engineered water management solutions in an environment where water is both scarce and unpredictable. These systems bear conceptual similarities to the underground aqueducts associated with the Nazca civilization, where precise gradients and long-distance planning were required to maintain water flow. The integration of hydraulic engineering with durable construction materials suggests a complex technological framework, one that challenges the traditional view of these societies as relying solely on simple or rudimentary methods. Perhaps the most compelling aspect of the Satura desert ruins is the persistent gap between observation and replication. Despite advances in material science, no modern reconstruction has fully matched the long-term resilience of the original structures under comparable conditions. This gap raises several possibilities. It may indicate the existence of specific techniques, such as precise mixing ratios, compaction methods, or curing sequences that have not been accurately reconstructed. Alternatively, it may point to environmental interactions that are difficult to reproduce in laboratory settings, such as the gradual effect of salt-laden winds over centuries. There's also the possibility that what we perceive as a single material is in fact the result of a dynamic process, evolving over time as the structure interacts with its surroundings. What do you think allowed the structures in Satura to survive for thousands of years in such an extreme environment? Simple accumulated experience over generations, or a form of lost ancient material technology? Share your thoughts in the comments below. Scattered across the stark, windswept desert plains of southern Peru, the geoglyphs of Pisco Valley geoglyphs stand as one of the most enigmatic and technically puzzling achievements of ancient human civilization. Yet, they remain overshadowed by the more widely known Nazca lines. Believed to have been created primarily by the Paracas culture between approximately 800 BCE and 100 BCE, these immense ground drawings may represent an earlier and more experimental phase of geoglyph construction, one that already demonstrates a level of spatial precision and conceptual planning that challenges modern assumptions about prehistoric societies. Unlike monumental stone architecture, these designs were etched directly into the desert itself by removing a thin upper layer of dark, not oxidized stones to reveal the lighter soil beneath, a method that, while simple in principle, becomes extraordinarily complex when executed across distances that can exceed several kilometers. The desert climate of the Pisco region, with annual rainfall often below 10 millimeters and minimal vegetation, has preserved these lines for over 2 millennia, allowing modern researchers to analyze their form and orientation with increasing accuracy using aerial photography, satellite imagery, and ground-based surveying techniques. What elevates the mystery of the Pisco Valley geoglyphs beyond mere scale and preservation, however, is the mounting evidence that many of these lines were not randomly placed, but instead exhibit deliberate and highly precise astronomical alignments, particularly with solar events such as the solstices, and field studies conducted from the 1970s onward, combined with more recent GPS-based research, have revealed that a number of the longest and straightest lines, some stretching between 1.5 and 3 kilometers, are oriented toward the points on the horizon where the sun rises or sets during the winter and summer solstices. In several documented cases, the deviation between the direction of a geoglyph line and the calculated solar azimuth at the time of construction is less than 1.5 degrees. To fully grasp the significance of this, one must consider the geometric implications. Over a distance of 2 kilometers, an angular error of just 1 degree would shift the endpoint of a line by approximately 35 meters. Yet many of these lines remain visually consistent and directionally stable across uneven terrain, suggesting that their creators were capable of maintaining alignment with a precision that rivals early historic surveying techniques. This level of accuracy becomes even more perplexing when we consider the technological limitations of the Paracas culture. There is no evidence that they possessed compasses, optical instruments, or written systems of trigonometry. Their tools, as inferred from archaeological findings, were likely limited to stone, wood, and simple measuring cords. One widely discussed hypothesis proposes that ancient builders used observational methods involving fixed points, placing stakes in the ground and tracking the position of the rising or setting sun over the course of a year, gradually refining the alignment through repeated observation. While this method is theoretically plausible, experimental reconstructions have shown that achieving and maintaining a straight line over more than 1 kilometre using only such tools is extremely difficult, particularly in a featureless desert where reference points are scarce and even slight deviations compound over distance. Furthermore, this approach would require not only technical skill, but also a long-term commitment to observation, implying a society capable of sustaining knowledge transmission across generations. Comparisons with other ancient civilizations only deepen the mystery. The builders of the Egyptian pyramids, for instance, achieved remarkable cardinal alignments, often within a fraction of a degree, yet they operated within a structured environment, using well-documented surveying tools such as merkets and sighting rods, and working on relatively confined construction platforms. In contrast, the creators of the Pisco geoglyphs worked across open desert landscapes, where maintaining a straight trajectory over kilometers without elevation control or stable reference markers would have been exponentially more challenging. Similarly, while the Nazca lines have long been associated with possible astronomical functions, most notably through the work of Maria Reicher, recent studies suggest that many Nazca lines may instead relate to ritual movement or hydrological symbolism. The Pisco Valley geoglyphs, however, appear to show a more selective and statistically significant pattern of alignment, with fewer motifs but greater directional consistency, raising the possibility that they served a more focused astronomical or calendrical purpose. Archaeological excavations in the broader Pisco region provide tantalizing but incomplete clues. Radiocarbon dating of associated Paraka settlements and burial sites confirms human presence during the period in which the geoglyphs were likely constructed, yet no direct tools or planning artifacts have been conclusively linked to the lines themselves. No large-scale layout diagrams, no remains of observational instruments, and no standardized units of measurement have been discovered, leaving researchers to reconstruct methodology indirectly through spatial analysis. Some studies have employed GIS modeling to simulate potential sightlines and solar alignments, suggesting that certain clusters of lines may have functioned as observational corridors, guiding the viewer's line of sight towards specific points on the horizon during key solar events. Others have proposed that the geoglyphs were part of ritual pathways, where participants walked along the lines during ceremonies timed to celestial cycles, effectively transforming the desert into a living calendar. Despite many hypotheses, the level of sophistication behind these geoglyphs remains difficult to fully explain. The combination of creating kilometre-long straight lines and achieving precise astronomical alignment suggests that ancient people possessed both geometric knowledge and a systematic understanding of the sky, something rarely seen in non-literate cultures. The presence of multiple parallel and intersecting lines also points to organized planning, possibly carried out over several generations. Ultimately, the biggest question remains: how did they achieve such precision, and more importantly, why was it necessary? Was it driven by religious beliefs, agricultural calendars, or a symbolic system we have yet to understand? Even after decades of research, the geoglyphs of Pisco Valley continue to stand as evidence of an ancient level of knowledge far beyond what we once imagined. Do you think these geoglyph lines were truly created to observe the sky, or to send a message to someone? Share your thoughts in the comments below. Hidden deep within the remote expanse of the Sahara Desert, in southeastern Algeria, the Tadrat Rouge rock formations rise like a silent archive of a forgotten world. their crimson sandstone towers and arches shaped into forms so refined that they often blur the line between natural erosion and deliberate design. At first glance, the landscape appears to be the predictable outcome of geological forces, wind abrasion, thermal stress, and sedimentary layering acting over millions of years. Yet the deeper one examines these formations, the more difficult it becomes to accept that randomness alone could produce such structural harmony. Some arches span more than 20 to 30 meters with remarkably consistent curvature, while vertical pillars maintain near-uniform proportions along their height, suggesting a level of symmetry rarely sustained in environments subject to highly variable wind directions and shifting sand. Geological models acknowledge that differential erosion can produce arches and balanced rock formations, but they also emphasize irregularity as a defining characteristic. In Tadrat Rouge, however, certain formations appear almost stabilized in their geometry, as though shaped under conditions far more controlled than the modern Sahara can provide. Yet the true enigma of Tadrat Rouge is not carved by wind, but by human hands that lived thousands of years ago during the African humid period, when this now hostile desert was a fertile savanna filled with lakes, rivers, and large fauna. Across the rock surfaces, thousands of petroglyphs have been documented, with estimated ages ranging between 10,000 and 5,000 years before present. These engravings were first systematically recorded during early 20th century expeditions, particularly by French explorers in the 1930s, and later expanded through extensive surveys associated with UNESCO programs in the late 20th century, which aimed to catalogue and preserve the broader rock art heritage of the region. What these studies revealed was not merely the presence of ancient art, but a level of technical execution that continues to challenge modern assumptions about prehistoric capabilities. Unlike shallow or irregular markings typical of many early petroglyph sites, the engravings at Tadrat Rouge often display controlled incision depth, consistent line width, and sharply defined edges, even after millennia of exposure to one of the harshest environments on Earth. Many figures, depicting giraffes, elephants, cattle, and human forms, extend up to 1 meter in length, with anatomical proportions rendered in a way that suggests both observational accuracy and practiced technique. Measurements taken from several panels indicate incision depths ranging from 2 to 6 millimeters, with minimal variation across individual figures, implying sustained control over force and angle during carving. Experimental archaeology has attempted to replicate such engravings using stone tools comparable to those available in the Stone Age, and the results are revealing. Producing a single deeply incised figure of comparable clarity can require anywhere from 5 to 20 hours of continuous labor, depending on the hardness of the sandstone and the desired precision. When multiplied across panels containing dozens of figures, the total labor investment becomes staggering, raising the question of whether efficiency techniques, now lost, were employed to accelerate the process. Even more puzzling is the durability of these carvings. The Sahara is not a passive environment, it is an active agent of erosion. Wind speeds in the region can exceed 50 kilometers per hour, carrying quartz-rich sand particles that function as natural abrasives, gradually wearing down exposed surfaces. Laboratory simulations suggest that fine details on sandstone should degrade significantly over a period of several thousand years under such conditions. Yet many Tadrat Rouge engravings retain crisp outlines and legible forms, despite being directly exposed for up to 10 millennia. This paradox has led researchers to explore the possibility of surface hardening phenomena. One hypothesis proposes that the rocks developed a protective patina through mineral deposition, such as iron oxides or silica, forming a thin, hardened layer that resists erosion. However, this does not fully explain why the carved lines, which initially would have disrupted this protective layer, remain so well preserved. In some cases, the engraved lines appear darker than the surrounding rock, suggesting differential weathering processes that may have, paradoxically, enhanced their visibility over time. Comparative analysis with other world-famous rock art sites further highlights the anomaly. In Lascaux Cave, dated to around 17,000 years ago, the artwork survives largely because it is protected within cave interiors, shielded from environmental degradation. In contrast, the engravings of Tassili Naja, located within the same broader region, often show greater degrees of weathering and less uniform incision despite similar ages. The contrast suggests that either the artisans of Tadrat Rouge employed more advanced or consistent techniques, or that local environmental conditions uniquely favoured preservation in ways not yet fully understood. Even when compared to carved stone traditions in later civilizations, such as the rock-cut architecture of Petra, the Tadrat Rouge petroglyphs remain striking, not for their scale, but for their resilience and the mystery surrounding their creation. Archaeological investigations in the late 20th and early 21st centuries have incorporated modern technologies such as high-resolution photography, three-dimensional laser scanning, and micro-erosion analysis to better understand these engravings. Some studies suggest that certain carvings may have been re-engraved or deepened over generations, indicating a long-term cultural engagement with specific rock surfaces. This practice could partially explain the uniform depth observed in some figures, as repeated tracing would gradually refine and stabilize the lines. However, this explanation introduces its own questions. How were these traditions transmitted across generations, especially during a period when the environment was undergoing rapid transformation from a humid ecosystem to an arid desert between roughly 6000 and 3000 BCE? The continuity of style and technique implies a level of social and cognitive organization that is difficult to reconstruct from the limited archaeological record. The imagery itself adds another layer to the mystery. The presence of aquatic and savanna animals, crocodiles, hippos, giraffes, confirms that the region once supported abundant water and vegetation, aligning with paleoclimatic data derived from sediment cores and fossil evidence. Yet the artistic consistency across changing environmental conditions suggests that the creators of these petroglyphs were not merely recording their surroundings, but participating in a symbolic or ritual tradition with deeper meaning. Some figures appear stylized or abstracted, hinting at belief systems or narratives that remain undeciphered. Without written records, these carvings stand as the only testimony of a culture that may have possessed both artistic sophistication and practical knowledge exceeding what is typically attributed to prehistoric societies. In your opinion, what is the greatest mystery of Tadrat Rouge, the stone carving techniques, or the possibility that ancient technologies have been lost to history? Share your thoughts in the comments below. In the remote heart of the Central Sahara within the territory of Libya, the immense volcanic plateau of Messak stretches across more than 6,000 square kilometers, forming a stark, black expanse of fractured basalt that resembles a petrified sea frozen in time. From the air, its surface appears almost unnatural, an endless field of dark, angular plates, broken and scattered, as if by some ancient cataclysm. Yet hidden within this seemingly lifeless terrain lies one of the most astonishing and least understood records of prehistoric human activity ever discovered. A vast, almost unimaginable collection of petroglyphs carved directly into the basalt itself, preserving a visual archive of a lost world and raising profound questions about the technological capabilities of early human societies. These engravings, numbering in the hundreds of thousands, depict a Sahara that no longer exists. Elephants with massive tusks, giraffes stretching their long necks, cattle herded in organized groups, and even hippopotamuses, animals that require abundant fresh water, are all rendered with striking clarity and anatomical precision. Their presence confirms what paleoclimatic studies have long suggested, that between approximately 10,000 and 5,000 BCE, the Sahara underwent a dramatic transformation known as the African Humid Period, during which it supported lakes, rivers, and grasslands capable of sustaining large animal populations. Archaeological expeditions, particularly those conducted by Italian teams led by researchers such as Savino di Lernia in the 1990s and early 2000s, thus documented tens of thousands of carvings across the Messak Plateau, with some estimates suggesting that the total number may exceed 500,000 when including undocumented regions. Radiocarbon dating of associated habitation sites and faunal remains places the majority of this artistic activity between 8,000 and 4,000 BCE, coinciding with the gradual desiccation of the region. Yet, while the subject matter of these carvings provides invaluable insight into prehistoric environments and cultures, it is the method of their creation that presents the greatest and most persistent mystery. Unlike many other rock art sites around the world, where carvings are made on relatively soft stone such as limestone or sandstone, the artisans of Messak Setafet worked almost exclusively on basalt, an igneous rock formed from rapidly cooled lava, characterized by its density and hardness, typically rated between 6 and 7 on the Mohs scale. This level of hardness places basalt significantly above the materials commonly used in ancient carving traditions and approaches the resistance of hardened steel. For comparison, the renowned petroglyphs of Valcamonica were carved into glacially polished sandstone and schist, materials that are far more susceptible to incision using stone or early metal tools. Similarly, the carvings at Altarock art, while impressive in their own right, were created on surfaces that are considerably softer and more forgiving than basalt. The implications of this difference are profound, and experimental archaeology has demonstrated that carving even a simple figure into basalt using primitive stone tools is an extraordinarily time-consuming and physically demanding process. Techniques such as pecking, repeatedly striking the surface with a harder stone, must be applied thousands of times to achieve even shallow indentations, to create the deep, clean lines observed in many Messak engravings, which often penetrate several millimeters into the rock, would require not only immense effort, but also remarkable control and consistency. Estimates based on replication experiments suggest that a single medium-sized engraving could require anywhere from 10 to 50 hours of continuous labor, depending on its complexity and depth. When multiplied across hundreds of thousands of carvings, and the total labor investment becomes almost inconceivable, suggesting a level of social organization and specialization that challenges conventional assumptions about prehistoric hunter-gatherer societies. Even more perplexing is the uniformity of execution observed across the plateau. Despite spanning hundreds of kilometers, many of the carvings share similar depths, line quality, and stylistic conventions, indicating that they were produced using standardized techniques rather than isolated experimental efforts. This consistency implies the existence of a transmitted body of knowledge, a technological tradition that was taught, refined, and preserved over generations. Yet, despite extensive fieldwork, archaeologists have struggled to identify the tools that would have made such precision possible. While lithic tools made from hard materials such as quartzite have been found in the broader region, they do not fully account for the level of detail and efficiency observed in the carvings. The absence of metal tools during the earliest phases of Messak's occupation further deepens the mystery. Metallurgy in North Africa did not become widespread until much later, meaning that the artisans responsible for these engravings likely relied entirely on stone-based technology. Some researchers have proposed that abrasive techniques, using sand and water to grind away the basalt surface, may have played a role, while others have suggested the possibility of thermal shock, in which the rock is heated and then rapidly cooled to induce microfractures that facilitate carving. However, these hypotheses remain speculative, as direct evidence for such methods has yet to be conclusively identified at Messak. What is undeniable is that the results achieved by these ancient craftsmen rival, and in some cases exceed, what can be easily reproduced even with modern tools, highlighting a gap in our understanding of their technological capabilities. Beyond the technical challenges of carving basalt, the spatial and contextual aspects of the Messak engravings add further layers of complexity. Many carvings are concentrated near ancient lake beds and watercourses identified through geological surveys, suggesting a close relationship between human activity and environmental resources. In some cases, the arrangement of figures appears to reflect not just artistic intent, but also ecological knowledge. With scenes of hunting and herding positioned in ways that correspond to natural terrain features. This has led some researchers to propose that the engravings may have functioned as a form of visual communication, or even environmental mapping, a way of encoding information about animal behavior, migration patterns, and resource distribution in a landscape that was constantly changing. As the African humid period came to an end around 5,000 years ago, the Sahara underwent a rapid and irreversible transformation. Lakes dried up, vegetation disappeared, and the once thriving ecosystems collapsed. The populations that had inhabited the Messak Plateau were forced to migrate, leaving behind their engravings as the only enduring evidence of their presence. Unlike later civilizations, they left no written records, no monumental architecture, and no clear cultural continuity that might help modern researchers interpret their work. What remains is a vast, silent archive, one that preserves not only images of a lost environment, but also the traces of a technological tradition that has vanished without a trace. How do you think ancient people at Messak Setafet managed to carve hundreds of thousands of images into extremely hard basalt with such precision? Leave your thoughts in the comments below. Hidden deep within the vast and largely uninhabited expanse of the Western Desert just south of the fertile depression known as Bahariya Oasis lies one of the most visually striking and scientifically puzzling landscapes in North Africa, the Black Desert Volcanic Hills. At first glance, the region appears to be a classic example of an ancient volcanic field shaped by eruptions that geologists date back roughly 20 to 30 million years during the Miocene epoch. Cone-shaped hills rise abruptly from the desert floor, their slopes covered in dark rock fragments, giving the entire region a burnt, almost artificial appearance. Yet beyond its dramatic visuals, the Black Desert presents a series of anomalies that continue to challenge conventional geological interpretations, particularly when it comes to one of its most defining features, the mysterious black coating that blankets nearly every exposed surface, raising questions that blur the line between natural processes and something that at times appears almost engineered. In standard geological theory, such coatings are categorized as desert varnish, a thin film composed primarily of iron and manganese oxides that accumulates over thousands to tens of thousands of years. The process is believed to involve a complex interaction between atmospheric dust trace moisture and microbial activity, with bacteria playing a role in concentrating manganese and iron on rock surfaces. However, extensive field surveys conducted throughout the late 20th century and into the early 21st century, particularly by Egyptian geological missions and international teams, have revealed that the Black Desert's coating deviates significantly from this model in both thickness and uniformity. While typical desert varnish layers rarely exceed 50 to 100 micrometers in thickness, Samples collected from multiple hills in the Black Desert have measured coatings reaching up to 200, and in some localized cases, even 300 micrometers. This is not merely a marginal difference. It represents a coating several times thicker than what is commonly observed in other hyper-arid environments. Equally striking is the consistency of the coating across different rock types and sizes. In comparative studies with regions such as the Atacama Desert and parts of the American Southwest Desert varnish, tends to form unevenly influenced heavily by microclimatic factors such as wind exposure, slope orientation, and water runoff. In those regions, it is common to find rocks that are only partially coated with clear gradients in coloration and thickness. In contrast, the Black Desert exhibits an almost unnerving uniformity. Large basaltic blocks, small pebbles, and even freshly exposed fragments revealed by ongoing wind erosion often display a complete and continuous black layer, as though each piece had been systematically treated. This level of homogeneity raises fundamental questions about the underlying formation mechanism. If microbial and environmental processes alone are responsible, how do they achieve such consistency across a landscape that spans dozens of square kilometers? Chemical analysis provides further insight but also deepens the mystery. Spectroscopic studies have confirmed high concentrations of iron oxides, particularly hematite, along with manganese compounds that contribute to the coating's deep black coloration. Trace elements including silica and clay minerals have also been detected, suggesting a complex depositional history. What is particularly noteworthy is the bonding strength between the coating and the underlying rock substrate. Laboratory abrasion tests indicate that the varnish in the Black Desert adheres with a force far exceeding that of typical desert varnish, resisting both mechanical wear and chemical dissolution. In modern materials, science creating a coating with similar durability would typically require controlled conditions involving elevated temperatures, pressure, or the use of chemical binders. Techniques such as thermal oxidation or industrial coating processes are used to produce protective layers on metals and ceramics. Yet these require precise regulation of environmental variables. The apparent natural formation of an equally robust coating, uniformly applied across an entire geological field, presents a paradox that is yet to be fully resolved. Adding to this complexity are observations of microstructures within the coating itself. High-resolution imaging has revealed layered growth patterns with alternating bands of varying composition, suggesting episodic deposition over extended periods. Some researchers have interpreted these layers as environmental records analogous to tree rings, potentially encoding information about ancient climatic conditions. However, the regularity of these layers combined with their uniform thickness across different samples has led others to speculate about more controlled formation processes. While such ideas remain on the fringes of mainstream science, they highlight the extent to which the Black Desert challenges existing frameworks. Beyond the coating, the geological context of the Black Desert introduces additional anomalies. Many of the volcanic cones exhibit remarkably consistent slopes, typically ranging between 30 and 40 degrees, which corresponds to the natural angle of repose for loose volcanic material. While this can be explained through natural processes, the similarity in size and shape among numerous hills has led to comparisons with artificially constructed mounds or engineered embankments. Satellite imagery further reveals that these cones are often arranged in clusters or semi-linear formations with relatively regular spacing. In tectonic geology, such patterns can result from underlying fracture systems or lines of weakness in the Earth's crust guiding the paths of volcanic eruptions. However, the clarity and repetition of these patterns in certain areas of the Black Desert have sparked ongoing discussions about whether additional factors may be involved. Thermal evidence within the rocks themselves adds yet another layer to the mystery. Certain basalt fragments display textures indicative of rapid heating and cooling, including vitrified surfaces and partially melted structures that suggest exposure to temperatures exceeding 1000 degrees Celsius. Yet unlike major volcanic regions, the Black Desert lacks extensive lava flows or large central craters that would normally be associated with such thermal activity. Instead, the evidence points toward more localized, possibly intermittent heat sources. Some geologists attribute this to small-scale eruptions and subsequent erosion that have obscured larger structures over millions of years. Others have proposed alternative mechanisms, including subsurface gas combustion or chemical reactions that could generate high temperatures in confined areas. While these hypotheses remain under investigation, they underscore the incomplete nature of current explanations. Archaeological interest in the region, while limited compared to Egypt's more famous sites, has also contributed to the intrigue. Surveys conducted in the vicinity of Bahariya Oasis have uncovered evidence of human presence dating back to the Paleolithic and Neolithic periods, including stone tools and habitation traces. Although no direct connection has been established between these early populations and the formation of the Black Desert's features, the proximity raises interesting questions about how ancient peoples might have perceived this landscape. To a prehistoric observer, the uniformly blackened hills shimmering under the desert sun could easily have appeared as something beyond the ordinary, perhaps even imbued with symbolic or ritual significance. When considered in a broader context, the Black Desert's combination of features, uniform coatings, consistent cone-shaped formations, evidence of high-temperature alteration, and patterned distribution places it among a select group of natural formations that challenge the boundary between geology and what might be described as proto-technological phenomena. Around the world, there are examples of natural structures that exhibit remarkable precision, such as the hexagonal basalt columns of the Giant's Causeway, or the precisely aligned stone formations at certain archaeological sites. However, what makes the Black Desert particularly compelling is the convergence of multiple such features in a single location, each reinforcing the impression of systematic processes at work. What do you think? Are these perfectly coated black rocks just a result of natural processes, or could they be evidence of a lost ancient material technology? Share your thoughts in the comments below. Hidden within the vast red deserts of southern Jordan, the petroglyphs of Wadi Rum form an immense open-air archive of human expression spanning more than 10,000 years. At first glance, these carvings, depicting camels, hunters, symbols and inscriptions, appear to be simple artistic traces left by nomadic cultures such as the Thamudic and Nabatean peoples. Yet a closer, more analytical examination reveals something far more complex. A body of work that challenges modern assumptions about prehistoric technology, craftsmanship, and environmental adaptation. While archaeologists have documented thousands of carvings across sandstone outcrops, cliffs, and boulders, the central mystery lies not in what is depicted, but in how these images were created with such precision, consistency, and durability under conditions that seem fundamentally hostile to controlled craftsmanship. Excavations and surveys conducted throughout the 20th and early 21st centuries, particularly by Jordanian and international archaeological teams, have catalogued petroglyph clusters positioned along ancient caravan routes and near long-vanished water sources. Radiocarbon dating of associated organic remains, combined with stylistic analysis, suggests that some carvings may date back to the late Neolithic period, around 8,000 to 12,000 years ago, while others belong to much later periods, including the Nabatean era, circa 1st millennium BCE to early centuries CE. Despite this broad chronological range, a striking feature persists. Many carvings, regardless of age, display remarkably uniform engraving depth, are typically between 2 and 5 millimeters, and exhibit clean, controlled lines with minimal evidence of erratic impact marks. This level of consistency is difficult to reconcile with the assumption that they were produced solely using rudimentary stone tools. To understand the anomaly, it is important to consider the material itself. Sandstone, while softer than igneous rocks like granite, still requires considerable force and precision to carve effectively, especially when attempting to produce smooth curves and consistent line depths. Experimental archaeology has attempted to replicate Wadi Rum style engravings using period-appropriate tools, flint chisels, hammerstones, and abrasive sand techniques. Results show that while it is technically possible, and the process is extraordinarily time-consuming, a single small figure may require several hours to complete, and even then, achieving the same uniformity seen in the original carvings proves difficult. Microfractures, uneven depths, and tool marks tend to accumulate, yet many Wadi Rum petroglyphs appear almost refined, as if produced with a controlled technique that minimizes such irregularities. This raises a fundamental question. Were these carvings truly the result of primitive, labor-intensive methods, or do they point to a more efficient, possibly lost technique? Some researchers have proposed that ancient artisans may have employed a combination of pecking and grinding, using fine sand as an abrasive medium to gradually erode the surface in a controlled manner. Yet others suggest repeated polishing could explain the smoothness of certain lines. However, these hypotheses do not fully account for the precision observed across large numbers of carvings, nor the apparent standardization in depth and style across different time periods and cultural phases. If such techniques were indeed used, they imply a level of procedural knowledge and skill transmission that is far more advanced than typically attributed to nomadic or semi-nomadic societies of the time. Comparisons with other major petroglyph sites deepen the mystery. At Tadrat Rouge rock formations, for example, engravings often show visible pecking marks and irregular edges, clearly revealing the mechanical process behind their creation. Similarly, at Tenere petroglyphs, tool marks and surface abrasions are more pronounced, allowing researchers to reconstruct the techniques used with greater confidence. In contrast, many Wadi Rum carvings lack these diagnostic traces, as though the process of their creation has been partially erased or was inherently more refined. This absence of clear tool signatures complicates efforts to reverse engineer the methods employed and suggest that either the tools were unusually effective or that post-carving environmental processes selectively smoothed the evidence. Another layer of complexity emerges when considering the role of natural chemical processes. Over millennia, exposed rock surfaces in desert environments develop a dark, mineral-rich coating known as desert varnish, or patina, composed primarily of manganese and iron oxides. Intriguingly, as many Wadi Rum petroglyphs exhibit high contrast between the carved lines and the surrounding surface, with the lines appearing lighter where the patina has been removed or has not yet fully reformed. In some cases, however, the patina seems to have partially recovered the lines in a way that enhances rather than obscures visibility, creating a kind of natural preservation effect. The rate at which this varnish forms is extremely slow, often measured in micrometers per 1,000 years, yet its distribution around certain carvings appears almost selective. This raises the possibility that ancient carvers may have understood, at least intuitively, how their interventions would interact with long-term geochemical processes, effectively designing images that would endure and even become more visible over time. Beyond the physical act of carving, the spatial distribution of the petroglyphs also hints at a level of planning that borders on proto-engineering. Many carvings are positioned at specific heights, orientations and angles relative to sunlight, such that they become most visible during particular times of day. Some are located along natural corridors through the desert, aligning with what are believed to be ancient migration or trade routes. This suggests that the creators were not merely leaving random marks, but were embedding information within the landscape itself, potentially functioning as navigational aids, territorial markers, or components of a broader symbolic communication system. The integration of carving technique, material properties, and environmental context points to a holistic understanding of both tool use and landscape dynamics. Archaeological campaigns in the region, including surveys supported by UNESCO and the Jordanian Department of Antiquities, have documented thousands of such carvings, yet no definitive toolkit or workshop sites have been uncovered that would explain their production at scale. This absence is particularly striking given the density of petroglyphs in certain clusters. If hundreds or thousands of carvings were produced over time, where are the discarded tools, the partially completed works, or the training sites that would normally accompany such activity? The lack of this supporting evidence adds weight to the argument that either the tools were made from perishable materials that have not survived, or that the techniques used were highly efficient and left minimal archaeological trace. Ultimately, the petroglyphs at Wadi Rum petroglyphs exist at the boundary between art and technology. While modern science suggests they were created using simple tools and gradually developed skills, their precision, consistency across millennia, and remarkable durability in such a harsh environment indicate that ancient people may have possessed techniques far beyond our current understanding. The real mystery is not just how they carved the stone, but how they achieved such extraordinary efficiency and long-lasting results. Until we can fully replicate these characteristics, Wadi Rum will remain an unanswered question in human history. Do you think the carvings at Wadi Rum petroglyphs were made using primitive tools, or are they evidence of a lost ancient technology? Share your thoughts in the comments below. Across the windswept basalt plains and arid steppe of Jordan and Syria lies one of the most perplexing and least understood engineering phenomena of the ancient world, vast geometric constructions known today as desert kite structures. At first glance, standing among them at ground level, there is almost nothing to see. Low lines of stone, often no more than half a metre to 1 metre high, stretch across the terrain in seemingly random directions, partially buried by sand, fractured by time, and indistinguishable from natural rock scatter. There are no towering walls, no monumental pillars, no inscriptions announcing their purpose. And yet this apparent simplicity conceals a staggering truth. These are not random remnants, but components of enormous, precisely organised systems that only reveal their true form when viewed from the sky. It was not until the early 20th century when Royal Air Force pilots flying over the Middle East began noticing strange kite-like patterns etched into the desert below that humanity first grasped the full scale of what had been hiding in plain sight for nearly 10,000 years. From an aerial perspective, desert kites transform into something entirely different. Massive, deliberate geometric figures composed of 2 or more elongated stone arms that converge toward a narrow enclosure or a sequence of deep pits. These arms can extend for extraordinary distances, often between several hundred meters and over 5 kilometers in length, with some of the largest documented examples exceeding this range when interconnected with neighboring systems. In certain regions, particularly across the Harat al-Sham volcanic desert spanning northeastern Jordan and southern Syria, satellite mapping has revealed dense clusters of these structures, forming networks that stretch across tens of kilometers. Recent large-scale surveys using high-resolution satellite imagery and drone-based photogrammetry have identified not just hundreds, but thousands of desert kites. Estimates now suggest that more than 5,000 may exist across the broader Middle East, with remarkable consistency in their layout and proportions. Such numbers alone imply a level of cultural continuity and shared knowledge that challenges traditional views of early Neolithic societies. What makes these structures profoundly mysterious is not simply their size, but the paradox of their design. They are engineered at a scale that demands spatial awareness far beyond the perspective available to their builders. Unlike modern engineers who rely on aerial surveys, GPS systems and precise instruments to maintain alignment over large distances, the creators of desert kites operated in a world without any form of elevated vantage point. From within the structure, a person would be unable to perceive its overall geometry. The long converging walls would disappear into the horizon, their intended meeting point invisible beyond the curvature of the terrain. And yet, when reconstructed through aerial imagery, these lines consistently converge with striking accuracy, forming angles that are neither arbitrary nor chaotic, but seemingly optimized. This raises a fundamental question. How did these ancient builders achieve such large-scale geometric coherence without ever being able to see the completed design? Comparisons with other ancient large-scale ground designs only deepen the enigma. The Nazca lines of Peru, for example, are often cited as a parallel case of geoglyphs, visible primarily from above. However, the Nazca culture dating to around 2,000 years ago likely employed grid systems, simple surveying techniques and elevated foothills to maintain proportions, methods supported by experimental archaeology. Desert kites, by contrast, predate the Nazca lines by several millennia, with radiocarbon dating placing many of them in the pre-pottery Neolithic B period, roughly 9,000 to 11,000 years ago. Moreover, while the Nazca lines are primarily symbolic or ceremonial, desert kites are functional systems embedded within the landscape requiring not only geometric planning, but also an understanding of animal movement, terrain and large-scale coordination. In this sense, they are closer in conceptual complexity to infrastructure projects than to artistic expressions, yet they lack any of the technological signatures we would expect from such undertakings. Archaeological excavations carried out over the past decades have provided crucial, albeit incomplete, insights. At several sites in Jordan, including those studied by international research teams in the early 21st century, investigators uncovered stone-lined pits at the terminal ends of the kite structures, some reaching several meters in depth. These pits are widely interpreted as traps designed to capture or kill animals driven along the converging walls. Faunal remains, including bones of gazelles and other herd animals, have been found in association with these features, supporting the hypothesis that desert kites functioned as large-scale hunting systems. However, even this explanation introduces new layers of complexity. The scale of the structures suggests that they were capable of funneling not just dozens, but potentially hundreds of animals at a time, implying coordinated hunting events involving large groups of people. Such operations would have required planning, communication and social organisation at a level rarely attributed to communities of this period. Furthermore, the construction itself poses significant logistical challenges. Building stone alignments stretching for kilometres would have required the movement and placement of vast quantities of material, even if each individual stone was relatively small. The labour investment alone suggests repeated use over long periods, yet many desert kites show signs of relatively brief or intermittent activity before being abandoned. Some structures appear unfinished, while others exhibit modifications or extensions, indicating that their builders were experimenting, adapting, or perhaps responding to changing environmental conditions. Climate data from the early Holocene period suggests that parts of the Middle East were once more hospitable, with greater vegetation cover and more abundant wildlife. As conditions became increasingly arid, the effectiveness of such large-scale hunting systems may have declined, contributing to their eventual disuse. Still, this does not fully explain the abruptness with which many of these structures seem to have fallen out of use. Another unresolved aspect concerns the apparent standardization across vast distances. Despite being separated by hundreds or even thousands of kilometers, many desert kites share similar configurations, long converging arms, narrow entrances and terminal enclosures or pits, suggesting either a shared cultural tradition or the independent discovery of an optimal design. If the former, it implies the transmission of complex architectural knowledge across wide regions without written language or centralized authority. If the latter, it suggests that different groups arrived at nearly identical solutions to the same problem, pointing to a deep intuitive understanding of geometry and animal behavior. In either case, the result is a landscape marked by patterns that are both highly functional and eerily uniform. Perhaps the most intriguing possibility is that we are only partially understanding the purpose of these structures. While the hunting hypothesis is supported by significant evidence, certain features do not fit neatly within this framework. Some kites lack sufficient pit depth to effectively trap large animals, while others are positioned in ways that seem suboptimal for herding. There is also growing speculation that certain desert kites may have served additional roles, perhaps as sites of ritual activity, territorial markers, or even early experiments in animal management and proto-domestication. If so, then their geometric precision and large-scale design may have carried symbolic as well as practical significance, encoding meanings that are no longer accessible to us. In the end, desert kite structures stand as a profound challenge to our understanding of early human capability. They demonstrate that long before the emergence of cities writing or formal engineering disciplines, human societies were already capable of organizing labor-manipulating landscapes and executing designs on a scale that rivals much later achievements. Their most defining characteristic, their immense coherent geometry, remained effectively invisible for millennia, hidden from ground-level perception and only revealed with the advent of flight. This alone suggests that their creators were working from a conceptual framework that did not depend on visualizing the whole, but on constructing it piece by piece according to rules or knowledge systems we have yet to fully reconstruct. Whether these rules were based on simple measurement techniques, accumulated experience, or something more sophisticated remains an open question. What is certain, however, is that desert kites are not merely relics of ancient hunting practices. They are evidence of a lost way of thinking about space scale and collective action, one that continues to elude complete explanation, even in the age of satellites and digital mapping. Hidden deep within the Sahara near the remote oasis of Farafra White Desert National Park presents a landscape so surreal that early explorers described it as a frozen sea of ghosts, a place where nature seems to have imitated intention, precision, and even design long before humans ever set foot in this region. Stretching across hundreds of square kilometers, the White Desert is composed primarily of chalk formations, soft, porous, sedimentary rock, formed from the compressed remains of ancient marine microorganisms dating back roughly 70 to 100 million years, when this entire region lay beneath a vast prehistoric ocean. Geological surveys conducted throughout the 20th and early 21st centuries, including sediment core analyses and fossil mapping expeditions, confirmed the marine origin of the material, revealing embedded shells, microfossils and layered deposits that align with late Cretaceous seabed conditions. Yet while the origin of the material itself is relatively well understood, the transformation of this soft rock into towering, highly structured formations remains far more difficult to fully explain. The dominant scientific explanation attributes the shapes to aeolian erosion, wind-driven abrasion, where sand particles act like natural cutting tools, gradually sculpting the rock over tens of thousands to millions of years. However, when examined closely, many formations challenge this explanation by exhibiting a level of geometric precision that appears inconsistent with purely chaotic environmental processes. Numerous pillars resemble perfectly balanced mushrooms, with narrow cylindrical bases supporting broad flat caps, sometimes measuring several meters in diameter. In some documented cases, field measurements have shown ratios between base width and cap width that remain strikingly consistent across different formations, often within a narrow proportional range that would typically require controlled shaping forces in engineered contexts. Even more puzzling are the smooth curvature transitions observed along these structures where concave and convex surfaces flow seamlessly into one another without the jagged irregularities commonly associated with natural erosion. To understand why this is so unusual, it is useful to compare these formations with known examples of human-engineered stonework. In ancient sites such as Petra Nabatean, builders used iron tools and controlled carving techniques to produce flat planes, symmetrical facades, and precise architectural proportions within sandstone cliffs. These features required deliberate planning, repeated measurement, and tool-based refinement. Yet in the White Desert, similar visual qualities, symmetry, balance, and smooth surface continuity appear without any evidence of human intervention, tool marks, or organized construction activity. Unlike Petra, where chisel lines and quarrying traces remain visible, the White Desert formations display surfaces that appear uniformly polished by natural forces, raising the question, how could wind, an inherently variable and chaotic system, replicate outcomes that in human contexts demand consistency and control? Further complicating the picture is the apparent stability of directional erosion over immense timescales. For such symmetrical shapes to form, the erosive forces would need to act in relatively consistent patterns, maintaining similar wind direction speeds and sand particle densities over extended periods. However, paleoclimatic reconstructions of the Sahara indicate that the region has undergone multiple dramatic climate shifts over the past several million years, alternating between arid desert conditions and more humid phases with vegetation and even lakes. These fluctuations would presumably disrupt any long-term uniform erosion pattern, yet the formations themselves suggest continuity rather than randomness. Some researchers have proposed that microvariations in rock density combined with localized wind vortices may have guided the shaping process, effectively creating natural feedback loops where erosion reinforces certain geometries over time. Still, these models remain incomplete and have yet to fully reproduce the level of precision observed in situ. Archaeological surveys conducted in and around the White Desert, while not uncovering evidence of human construction, have provided additional context that deepens the mystery. Expeditions in the Farafra region have documented prehistoric human presence dating back tens of thousands of years, including stone tools and temporary habitation sites, indicating that early humans witnessed at least some stages of the desert's transformation. Yet there is no indication that these populations possessed either the technology or the intent to shape the formations themselves. Instead, their remains serve as a chronological marker, confirming that many of the structures predate known human activity in the area. Geological dating techniques, including stratigraphic analysis and fossil correlation, further support the conclusion that the formations evolved gradually over immense timescales, rather than being the result of sudden or artificial processes. Perhaps the most intriguing aspect of the White Desert lies in what might be called its organized randomness. While each formation is unique, clusters of rocks often appear distributed with subtle regularity, maintaining comparable spacing and orientation across certain regions. Satellite imagery and aerial surveys have revealed patterns that, while not perfectly ordered, suggest underlying environmental constraints shaping the landscape in a semi-coherent way. This balance between chaos and structure is precisely what makes the geometric precision of individual formations so difficult to dismiss as mere coincidence. In engineering, achieving such balance typically requires iterative design and feedback control. In nature, it implies the presence of governing processes that operate with far greater subtlety than previously understood. Ultimately, the White Desert stands as a reminder that not all precision is the product of intelligence in the human sense, yet not all natural formations can be easily reduced to randomness either. It exists in a grey zone where geology begins to resemble design, where erosion mimics intention, and where the limits of current scientific models become visible. The question is no longer simply how wind and sand carve these shapes, but whether the processes involved include layers of complexity that remain undiscovered. In this sense, the White Desert is not just a geological curiosity, it is a natural phenomenon that challenges our assumptions about order symmetry and the hidden capabilities of the Earth itself, leaving open the possibility that what we perceive as impossible precision may one day be understood as part of a deeper, still unfolding science of planetary processes. Across the vast windswept deserts of northwestern Saudi Arabia, particularly in the AlUla region, lies one of the most quietly astonishing archaeological discoveries of the modern era, the Mustatil structures, elongated low-profile stone rectangles that stretch across the landscape like faint scars of a forgotten civilization. First identified through satellite imagery and aerial surveys in the early 2000s, and later systematically studied by teams working with the Royal Commission for AlUla and international research groups, these structures have since been recognized as some of the oldest large-scale stone constructions on Earth, dating back to approximately 5,000 to 5,500 BCE. This places them more than 2,000 years before the pyramids of Giza and significantly earlier than Stonehenge, fundamentally challenging long-standing assumptions about when and how complex construction practices emerged in human history. Today, over 1,000 Mustatil have been documented, forming a dense and deliberate network across a region that during the early Holocene was not the barren desert we see today, but a greener environment with seasonal lakes, grasslands, and thriving pastoral ecosystems. At first glance, the Mustatil appear almost underwhelming simple arrangements of stone walls forming long rectangles, sometimes exceeding 600 meters in length, but rarely rising more than 1 to 2 meters in height. Yet this apparent simplicity is precisely what makes them so perplexing. Unlike later monumental architecture that relies on finely cut stone blocks, complex joinery, or monumental verticality, the Mustatil are built from locally sourced unworked stones, gathered from the surrounding terrain and stacked to form continuous walls. There is no mortar binding the stones, no evidence of carved joints or precision-cut blocks, and no indication of advanced tools such as metal implements. And yet, despite these limitations, many of these walls have remained structurally intact for over 7,000 years, resisting erosion, temperature fluctuations, and the relentless forces of desert winds. This brings us to the most compelling and least understood aspect of the Mustatil, their construction technique, which represents a form of engineering that is at once primitive in materials, yet highly effective in execution. From a modern perspective, building a structure that extends hundreds of meters in a straight line, without laser alignment, surveying instruments, or even standardized measurement systems would require careful planning and coordination. Archaeological surveys have shown that many Mustatil walls maintain a remarkable degree of linear precision, with only minimal deviation across their entire length. This suggests that their builders employed some form of systematic alignment method, possibly using visual sight lines, rope measurements, or coordinated human positioning to maintain direction over long distances. When compared to other ancient construction traditions, such as the polygonal masonry of the Inca or the astronomically aligned stones of Stonehenge, the Mustatil stand apart not because they are more refined, but because they achieve scale and durability through minimalism. Excavations carried out between 2018 and 2022 have provided critical data that both illuminate and complicate our understanding of these structures. Within several Mustatil enclosures, archaeologists uncovered concentrations of animal remains, particularly cattle skull fragments, often deliberately placed near the structure's terminal platform, sometimes referred to as the head of the rectangle. Radiocarbon dating confirms that these remains are contemporaneous with the construction of the structures, indicating that they were not deposited randomly, but were part of intentional ritual practices. In some cases, the bones appear to have been carefully arranged, suggesting ceremonial deposition rather than simple disposal. However, what is notably absent is any evidence of long-term habitation. There are no hearths, no domestic tools, no signs of permanent settlement. This strongly supports the hypothesis that Mustatil were ritual or ceremonial sites, possibly used for communal gatherings, animal offerings, or early forms of religious expression tied to environmental cycles such as rainfall or seasonal migration. Despite this emerging interpretation, the scale of construction remains difficult to reconcile with what we know about Neolithic societies in the region. Each Mustatil would have required the collection, transport, and placement of thousands of stones, a task that implies not only significant labour investment, but also a high degree of social organisation and coordination. To replicate this process across more than 1,000 sites suggests the existence of a shared cultural framework, perhaps even a network of communities bound by common beliefs or traditions. Yet unlike later civilizations, there is no written record, no iconography, and no centralized architecture that might point to a governing authority or organized state. What we are left with is a pattern of construction that is both widespread and standardized, yet anonymous in its origin. From an engineering standpoint, the Mustatil can be seen as an early example of what modern designers might call low-tech, high-resilience architecture. By relying on abundant local materials, minimizing vertical load, and emphasizing horizontal expansion, the builders created structures that are inherently stable and resistant to environmental stress. The low height of the walls reduces the risk of collapse, while the broad base distributes weight evenly across the desert ground. The use of unworked stones rather than precisely cut blocks allows for flexibility in construction and easier replacement or adjustment during the building process. In essence, the Mustatil do not resist the environment. Through strength alone, they adapt to it, using simplicity as a form of durability. This stands in stark contrast to later monumental structures, where increasing complexity often introduces structural vulnerabilities that require maintenance or reinforcement. When compared to other ancient sites, the uniqueness of the Mustatil becomes even more apparent. The pyramids of Egypt, for example, represent a triumph of centralized power, requiring tens of thousands of laborers, advanced planning, and precise stone-cutting techniques. Stonehenge, on the other hand, reflects a deep understanding of astronomical cycles and the ability to transport massive stones over long distances. The Mustatil, by contrast, achieve their impact through repetition and distribution rather than height or mass. They're not designed to dominate the skyline, but to extend across the land, subtle, almost invisible from ground level, yet unmistakably deliberate when viewed from above. This has led some researchers to question whether their layout may have had a spatial or symbolic meaning that is not immediately apparent from a human-scale perspective. The Mustatil structures have reshaped how we understand the capabilities of ancient humans. Even without metal tools, writing, or urban civilizations, they were able to construct large-scale structures with remarkable precision and durability. These constructions reflect an engineering mindset that prioritized efficiency, adaptability, and harmony with the environment over complexity. However, many critical questions remain unanswered. How were they designed and aligned? How did people at the time organize labor on such a scale? And why did this tradition emerge and then disappear so mysteriously? Amid the deserts of Saudi Arabia, the Mustatil still stand as traces of a forgotten engineering philosophy, one that may go far beyond what we currently understand. In your opinion, are the Mustatil the result of simple yet intelligent engineering, or the remnants of an ancient knowledge system we still don't fully understand? Share your thoughts in the comments below. In the heart of the Sahara, within the remote and unforgiving expanse of the Tenere Desert, there once existed a phenomenon so improbable that it has continued to challenge scientific reasoning decades after its disappearance: the legendary Tree of Tenere. Often described by explorers as the most isolated tree on Earth, it stood alone in a landscape where life, by all measurable standards, should not exist. With no other vegetation recorded within a radius exceeding 300 kilometers, and with environmental conditions defined by extreme aridity, annual rainfall rarely surpassing 10 to 20 millimeters, and temperatures frequently climbing above 50 degrees Celsius, the survival of this single acacia was not just unusual, it was in many respects scientifically paradoxical. First documented in detail by French military expeditions in the early 20th century and later examined during multiple scientific surveys in the 1930s, 1940s, and especially the 1959 hydrological excavation, the tree quickly became a subject of fascination not only for its symbolic isolation, but for the deeper, unresolved questions it posed about the limits of life. At first glance, the explanation for its survival appeared to lie underground. The 1959 excavation conducted by French researchers revealed that the tree's root system extended to astonishing depths of approximately 35 to 40 meters, tapping into a subsurface water source. This finding, while remarkable, did not resolve the mystery. It intensified it. In known botanical models, not even the most drought-resistant plants such as prosopis species, mesquite, rarely extend their roots beyond 15 to 20 meters. The energetic cost of developing and maintaining a root network twice that depth would require a level of metabolic efficiency far beyond what is observed in desert flora. Furthermore, geological analyses of the surrounding region failed to identify a stable, renewable aquifer capable of sustaining such a system over decades, let alone a century. In other words, the very mechanism proposed to explain the tree's survival seemed to contradict established principles of plant physiology and hydrology. Attempts to contextualize the tree within the broader environmental history of the Sahara introduce yet another layer of complexity. During the African humid period, approximately 5,000 to 10,000 years ago, the region now known as the Tenere Desert was a vastly different landscape, one characterized by lakes, rivers, and savanna-like ecosystems capable of supporting diverse plant and animal life. Some researchers have suggested that the Tree of Tenere might represent a lingering remnant of this ancient green Sahara, a biological survivor that persisted long after the climate shifted toward hyper-aridity. However, this hypothesis encounters significant contradictions. No archaeological or paleobotanical evidence, such as fossilized root systems, pollen concentrations, or remnants of surrounding vegetation, has been found in the immediate vicinity to support the existence of a former localized ecosystem. Moreover, genetic comparisons with extant acacia species indicate lifespans far shorter than the thousands of years required to bridge the humid period to the present, suggesting that the tree could not have simply survived continuously from that era. It is precisely at this intersection of contradiction where known explanations fail to fully account for observed reality, that the most compelling and controversial hypothesis emerges: that the Tree of Tenere may have embodied a form of natural biotechnology that operates beyond current scientific understanding. Unlike typical xerophytic adaptations such as reduced leaf surface area, thick cuticles to limit water loss, or CAM, crassylation acid metabolism, photosynthesis to optimize water use, the survival strategy of the Tenere tree appears to have involved a far more sophisticated and efficient system. One possibility is that the tree possessed an unprecedented ability to regulate transpiration at the cellular level, effectively minimizing water loss to near zero under extreme heat conditions. Another hypothesis suggests the existence of specialized root membranes capable of extracting not only liquid water, but also microscopic traces of moisture bound within mineral substrates, an ability that, if verified, would represent a fundamentally new category of plant-water interaction. Comparative analysis further highlights the extraordinary nature of such a capability. The Welwitschia mirabilis of the Namib Desert, often cited as one of the most resilient plants on Earth, survives for over 1,000 years by capturing fog moisture from coastal air currents. Similarly, cacti in the Sonoran Desert employ highly efficient water storage tissues and spiny exteriors to reduce evaporation. Yet both examples rely on at least some predictable environmental inputs: fog cycles, seasonal rainfall, or humidity gradients. In stark contrast, the Tenere region offers none of these advantages. There is no consistent fog, no reliable precipitation, and minimal atmospheric moisture. If the Tree of Tenere indeed survived through mechanisms analogous to these plants, it would imply a level of efficiency so extreme that it borders on the theoretically impossible within current biological frameworks. Field reports from mid-20th century expeditions provide additional, albeit indirect, support for the uniqueness of the phenomenon. French Foreign Legion patrols, as well as scientific teams traversing the Sahara, repeatedly documented the tree as a solitary landmark used for navigation, a fixed point in an otherwise featureless landscape. These accounts consistently emphasize not only its isolation, but the complete absence of ecological support systems in its vicinity. No undergrowth, no insect activity, no signs of symbiotic relationships typically associated with plant survival were observed. This absence raises a critical question. How could such a complex organism sustain itself without the microecosystem interactions that most plants depend on? Despite advances in modern science, efforts to replicate the tree's survival conditions in controlled environments have yielded no success. Experimental attempts to grow acacia species under simulated Tenere conditions, extreme heat, minimal water input, and deep-root irrigation have consistently resulted in failure, with plants unable to maintain metabolic balance beyond relatively short periods. This inability to reproduce the phenomenon suggests that the Tree of Tenere may have relied on a unique convergence of factors: genetic anomalies, precise geological conditions, and perhaps even unknown microbial interactions that are not easily recreated. The destruction of the tree in 1973, when it was struck by a vehicle in one of the most remote regions on Earth, represents a profound loss not only of a natural icon but of a living scientific puzzle. At the time, technologies such as genomic sequencing, isotopic analysis, and advanced microscopy were not available to the extent they are today. As a result, the opportunity to study the tree at a molecular and cellular level, potentially uncovering the mechanisms behind its extraordinary resilience, was lost forever. Today, a metal sculpture marks its former location, serving as a symbolic replacement, but offering no answers to the questions that once surrounded the original organism. Do you think the Tree of Tenere was simply an extreme natural phenomenon, or evidence of a biological mechanism we still don't understand? Share your thoughts in the comments below. Spanning the vast hyper-arid landscape of the Atacama Desert, the desert geoglyphs of Atacama stand as one of the most extensive and least understood large-scale human interventions ever inscribed onto Earth's surface. A silent network of symbols stretching across more than 150,000 square kilometers and comprising over 5,000 identified figures. Unlike the more iconic Nazca lines, which are concentrated within a relatively confined pampa and largely etched into flat terrain. The Atacama geoglyphs are scattered across hillsides, slopes, ridges, and desert plains, forming a complex visual system that appears to interact directly with the natural topography. Some figures reach lengths of 80 to 100 meters, yet many are positioned in such a way that they are not fully legible from ground level, thus suggesting that their creators operated with a spatial awareness that extended beyond immediate human perspective. Archaeological investigations beginning in the mid-20th century and expanding through systematic surveys in the 1960s, followed by satellite mapping and drone-based documentation in the 21st century, have dated the majority of these geoglyphs to between 600 CE and 1500 CE, overlapping with pre-Inca and Inca cultural phases. Despite this growing body of data, the fundamental question of how these ancient societies achieved such consistent, large-scale precision with seemingly limited technological means remains unresolved. At first glance, the construction techniques appear deceptively simple. Researchers have identified three primary methods: the extractive technique, in which the dark oxidized desert surface, known as desert varnish, is carefully removed to reveal lighter soil beneath; the additive technique, where stones are deliberately arranged to form lines and shapes, and a mixed approach combining both strategies. Yet this apparent simplicity collapses under closer scrutiny. Many lines remain remarkably straight over long distances, deviations are minimal even across uneven terrain, and geometric forms retain proportional integrity despite being executed on sloped surfaces where visual distortion would naturally occur. Experimental archaeology has demonstrated that it is theoretically possible to produce straight lines using rudimentary tools such as wooden stakes, cords, and line-of-sight alignment methods. However, these reconstructions typically occur under controlled conditions and often require iterative corrections, processes that would be difficult to replicate consistently across thousands of geoglyphs distributed over vast distances. Crucially, no standardized measuring tools, no preserved grid systems, and no physical planning templates have been conclusively identified at Atacama sites, creating a profound disconnect between the observable precision of the geoglyphs and the apparent absence of the instruments needed to produce them. This paradox becomes even more striking when the environmental context is considered. The Atacama Desert is widely recognized as the driest non-polar desert on Earth, with some regions experiencing decades without measurable rainfall. And while this extreme dryness has played a key role in preserving the geoglyphs for over a millennium, it does not explain their creation. To construct figures of such scale, often exceeding 100 meters in length, on sloped or irregular terrain would require not only careful planning, but also a system for maintaining consistent proportions without the benefit of aerial observation. In modern engineering, such tasks would typically involve scale drawings, surveying instruments, and iterative measurement. Yet no evidence suggests that such tools existed in the Atacama region during the relevant period. Some scholars have proposed that builders may have used elevated vantage points, aligning their designs with distant landmarks such as mountain peaks, or employed temporary markers to guide construction. Others suggest the use of proportional systems based on repeated units, perhaps lengths of cord or standardized body measurements, allowing for the scaling of designs from smaller models to larger ground layouts. While plausible, these hypotheses remain speculative in the absence of direct archaeological confirmation. It is within this gap between observed outcome and missing evidence that the most compelling mystery emerges. The possibility that the creators of the Atacama geoglyphs relied on a non-material or perishable system of measurement and design, one that has left little trace in the archaeological record. The repetition of certain geometric motifs across distant sites suggests the existence of shared design conventions, implying a level of standardization that would typically require formalized measurement systems. Yet unlike ancient Egypt, where measuring rods and construction guidelines have been preserved, or the Roman world, where surveying instruments and written engineering treatises survive, the Atacama region offers no such artifacts. This raises the possibility that technological knowledge here was embedded in practice rather than tools, transmitted through oral tradition, apprenticeship, and embodied skill rather than written or material systems. In such a framework, precision would not be achieved through instruments, but through refined techniques internalized by the builders themselves, a form of human calibration that modern archaeology struggles to detect. Comparative analysis further highlights the uniqueness of the Atacama geoglyphs. The Nazca lines, for example, also demonstrate large-scale precision without aerial technology, but they are predominantly executed on flat surfaces, simplifying issues of alignment and proportion. In contrast, Atacama geoglyphs frequently occupy sloped terrain, where maintaining geometric consistency would require compensating for perspective distortion, an advanced conceptual challenge even by modern standards. Similarly, when compared to Inca infrastructure, such as road networks and terrace systems, which exhibit remarkable engineering precision and integration with the environment, the geoglyphs appear to function as a visual and symbolic extension of these systems, possibly serving as navigational markers, ritual pathways, or territorial indicators. Indeed, several geoglyphs depicting llama caravans align with known trade routes that connected highland and coastal regions, supporting the hypothesis that they played a role in guiding movement across the desert. However, even if their function can be partially reconstructed, the methods by which they were designed and executed remain elusive. Archaeological efforts have provided important but incomplete insights. Field surveys conducted throughout the late 20th century documented the distribution and typology of geoglyphs, while more recent technologies, such as high-resolution satellite imagery and drone-based photogrammetry, have allowed researchers to map their spatial relationships with unprecedented accuracy. These soil and material analyses have confirmed the presence of desert varnish and have suggested that ancient builders may have intentionally manipulated surface conditions to enhance contrast and durability, indicating a sophisticated understanding of environmental processes, what might be described as an early form of applied geochemistry or proto-material science. Yet even these findings do not resolve the central question of measurement and planning. The absence of construction debris, tool marks indicative of specific instruments, or staging areas further complicates attempts to reconstruct the building process. Do you think the builders of the Atacama geoglyphs used only simple tools? Or did they possess a lost system of measurement we have yet to rediscover? Share your thoughts in the comments below. Rising in stark isolation within the desert expanse of Hegra, the monumental structure known as Qasr al-Farid, translated as the Lonely Castle, stands as one of the most technically perplexing relics of the Nabatean civilization. Carved entirely from a single sandstone outcrop, approximately 22 meters in height, this unfinished tomb has become a focal point for archaeologists attempting to understand not only Nabatean artistry, but also the deeper engineering logic that guided their construction methods. Excavation campaigns and surveys carried out over the past century, particularly those intensified after Hegra was designated a UNESCO World Heritage Site in 2008, have established that the structure dates to the 1st century CE, a period of economic and cultural peak for the Nabateans. Yet despite advances in archaeological methodology, including high-resolution 3D scanning, stratigraphic analysis and geological mapping, Qasr al-Farid continues to resist full explanation. Its greatest mystery lies not in its decorative style, but in the method of its creation, a top-down carving technique that appears both deliberate and extraordinarily difficult to execute under ancient conditions. At first glance, the monument's facade presents a familiar Nabatean aesthetic: symmetrical pilasters, a stepped crowning motif, and a central doorway carved into the rock. However, a closer inspection reveals a striking inconsistency. The upper portions of the facade are far more refined than the lower sections, where rough, incomplete surfaces and visible chisel marks dominate. This vertical gradient of completion has been confirmed through multiple field studies and surface examinations, leading researchers to conclude that the carving process began at the top of the rock and progressed downward. Such a method, while theoretically advantageous in preventing debris from damaging finished sections, introduces a series of logistical challenges that are difficult to reconcile with the technological limitations of the time. How did ancient workers access and stabilize themselves at the top of a 22-meter monolith standing freely in open terrain? Unlike cliff-carved structures where natural ledges or plateaus can facilitate access, Qasr al-Farid offers no such advantage. It is a solitary block surrounded by flat desert devoid of any permanent architectural support system. Archaeological investigations have searched extensively for evidence of scaffolding post holes, anchor points, or remnants of structural supports, but findings remain inconclusive. Some researchers propose that wooden scaffolding systems were erected around the rock, possibly reinforced with rope networks and anchored at ground level. However, given the arid environment of AlUla, any organic materials would have long since decomposed, leaving little trace. Experimental archaeology has attempted to recreate such scaffolding using period-appropriate materials, suggesting that a multi-tiered wooden framework could have supported workers as they carved downward. Yet these reconstructions often struggle to replicate the precision observed in the upper carvings, where alignment errors are minimal and decorative elements maintain consistent proportions across several meters. In some measured sections, deviations from symmetry are less than a few centimeters, an astonishing level of accuracy for a process conducted at height without modern measuring instruments. Comparative analysis with other Nabatean sites provides additional context, but also deepens the mystery. In Petra, for example, many rock-cut facades exhibit evidence of top-down carving, yet these are typically integrated into cliff faces that allow access from above. Pathways, natural terraces, and even carved steps have been identified in Petra, suggesting a more straightforward logistical framework. At Qasr al-Farid, no such features exist. The isolation of the rock implies that any top-down approach would have required a fully engineered access system, one that could support not only the weight of workers, but also their tools and possibly even water supplies necessary for stone carving in a desert environment. The absence of direct evidence for such systems has led some scholars to question whether alternative methods such as earthen ramps or sand embankments may have been used to reach the upper sections. However, these hypotheses face their own limitations. Constructing a stable ramp to a height of over 20 meters would require a significant volume of material and labor, and yet no clear traces of such large-scale earthworks have been identified in the immediate vicinity. Further insight comes from the analysis of tool marks across the structure. Microscopic studies indicate that iron chisels were the primary tools used, consistent with known Nabatean metallurgy. However, the distribution and quality of these marks vary significantly between the upper and lower sections. The upper carvings display fine controlled incisions suggesting the work of highly skilled artisans, while the lower areas exhibit broader, less refined cuts. This has led to the hypothesis that the most experienced craftsmen began the project at the top, establishing the overall design and critical proportions before passing the work to less skilled labourers as the process continued downward. Alternatively, the shift in quality may reflect a sudden interruption in construction, possibly linked to historical events such as the Roman annexation of the Nabatean kingdom in 106 CE. Geological surveys have also identified natural fissures within the sandstone, raising the possibility that structural instability may have contributed to the abandonment of the project before completion. What makes Qasr al-Farid particularly valuable to researchers is precisely its unfinished state. Unlike completed monuments, which often conceal the stages of their construction, this structure preserves a snapshot of the building process in progress. The visible transition from refined to rough surfaces provides a rare opportunity to study ancient techniques in situ. Yet even with this advantage, the core question remains unresolved. How did the Nabateans coordinate and execute a top-down carving process on such a scale with such precision? The absence of written records compounds the difficulty. While civilizations such as the Romans left detailed accounts of their engineering practices, the Nabateans have left behind little more than inscriptions and material remains, offering few direct clues to their methods. In a broader comparative framework, Qasr al-Farid invites parallels with other monolithic constructions around the world, such as the rock-hewn churches of Lalibela in Ethiopia, or the cave complexes of Ellora in India. These sites also demonstrate advanced stone carving techniques often involving vertical excavation or top-down approaches. However, they differ in one crucial aspect: they are typically embedded within larger geological formations or supported by surrounding terrain. The complete isolation of Qasr al-Farid sets it apart, suggesting a level of logistical planning and engineering adaptation that is not fully understood. Even when compared to Egyptian rock-cut tombs or temples, where scaffolding and ramp systems have been more thoroughly documented, the Nabatean example remains anomalous. Qasr al-Farid is a paradox, unfinished yet remarkably precise, isolated yet reflecting the advanced engineering of the Nabateans. Although clearly visible, its construction, especially the top-down carving technique, remains unexplained. In the silence of the desert, this structure is not just a tomb, but an unanswered question stretching from the top of the rock to the limits of human understanding. In your opinion, how did the Nabateans actually manage to carve this structure from the top down with such astonishing precision? Was it simply a lost ancient technique, or is there something we still don't fully understand? Share your thoughts in the comments below.